Good afternoon, everyone. I'm Álvaro González Jiménez. I'm a board member of the MICCAI RISE Society, and I'm pleased to introduce our speaker today, Eric Kerfoot, is a software architect in the Department of Biomedical Engineering at the King's College of London. And Eric has led software development across different internal projects and international collaborations, like the project of Monite that some of you might know. He has a background in biomedical imaging and a doctorate from Oxford in software engineering. Today, he will give a practical introduction to Git and Docker, which is very important for the development of your research and a correct deployment for the reproducibility of your results. If you have any question during the session, please type it down in the Q&A section, and we will answer it in the end of the session. So without further ado, please join me in welcoming Eric. And thank you so much.
Great. Thank you very much for the intro. So yes, I'm Eric. We'll be going over a very, very brief overview of Git and Docker. These are very deep topics, and we'll be going into very light details for the purposes of what you're doing this week in the summer school. So these are two very different technologies as well. They have not very much in common really, but they are two collaborative and software development tools that really do make sense for in general for development of systems, for deployment of systems, certainly, and just for collaboration with other people. So we'll be talking through just the basic usages of these to put together a very simple system for yourselves. So Git is a tool for managing versioning of source code. Typically, it could be used for versioning anything really. The idea with this is to have some place where we are going to have a system for managing differences in a set of code objects. So how we handle the differences between different versions of text files for the most part. And then that's useful for keeping track of when things have changed in your source repository, when other people are collaborating with you and are contributing their changes to your repository, when you are managing different features being done for your code, and then you have different people working on those and they want to eventually integrate what they're working with together. This is something that'll be less relevant to you today, so I'm going to gloss over to a huge degree a lot of that branching behavior and just talk about how to set up a Git repo and then how to use that repo with Docker. In particular, that will be done in the materials that are in the repo that have been sent to you now. So secondly, Docker is a containerization technology. So this is a way of defining what is essentially a running system. So you want to produce a Docker image, which contains all the information, all the files, all the setup for running an application for your usage at least. And this is what looks like internally a Linux system, but it doesn't have some of the features that actually would make it sort of a virtual machine. So it doesn't have a kernel, it doesn't have interaction directly with hardware, explicitly at least. So this is something where it's a bit more lightweight than a virtual machine, but a lot better than just a simple environment like what you do with Conda or the virtual environment. So it's something that's in the general case is used for containerization in a broad sense of the term. So these are both very important. We'll get into these. So first up, we talk about Git. This is a technology for, as I say, working with source version control. So the idea with this is that we are going to be using Git to manage a repository, which is going to be a directory of files. These files are going to be the source files for your project, for your software system. And then the Git will be used to manage when you change files, when you are adding code or fixing things or modifying things in some other way, and then keeping track of that history over time. What Git does is it will have within a directory a .git subdirectory, and that will contain all the metadata about change. So that will contain information about what's going on with what's internal to the changes of files over the history of that repository, and it will not contain the actual data itself about your files. That will still be in the main high-level directory. And then there'll be things that will be in that Git about configuration and about pointers to remote things in different places. So we'll talk about what's in that later on, but typically the .git directory is something you don't mess with yourself personally, so I wouldn't worry about it. So the installation, you have these slides, I do hope. There's a lot of information on the internet about how to install it for different operating systems, so I'm not going to go into that here. On the main Git page, there is downloads for all the different operating systems. When using Git, I do recommend you use a GUI tool, something like Git Ahead, which is free and open source. This helps you manage the actual Git operations as well as visualize change over time in your repository. And they are very useful tools for understanding what's going on. The command line tools can be quite confusing sometimes, honestly, and some of the terminology is a bit weird. So I would generally recommend going with a GUI tool and then just see what it does, understand the concepts, and go from there. Installation for Ubuntu is there, but as I say, I would refer to what the instructions are in the repository. So it's important with Git to get concepts correct very early on. As I said earlier, the concepts are sometimes badly named, and it can be quite confusing what's going on. So the key thing is that Git is going to track changes to source files over time. And what that means is that there's going to be certain states that Git is going to recall that you explicitly, commit as a state. That state is going to represent the change from the parent states to the current state, and it's going to recall those relationships over time. So whenever you modify your repository and then commit that state, that is going to be essentially a node in a graph. And every node is going to have, just about every node at least, is going to have a parent. And so that the state of the repository for that node represents all the changes for all the parents put together to that point in time. And then with branching, of course, you can start from a node and then create new changes that are different from other changes from that node. And so you can have two different changes that are essentially parallel with one another, and they could represent different features or different experiments with different pieces of code that change the same lines. And so they may conflict in a manner, but they're kept separately and their history is kept separately. So to illustrate that, if we look at just this simple diagram here, this is going to be very similar to a lot of diagrams that you'll see trying to explain Git. But each little node, each little circle here represents a state of the system essentially. So we start with state A and then we make some changes, commit those, that becomes state B, and state B's parent is just A. We can tag state B as being version 1 of our system, and then we can move on to doing other changes. So state C might be something different again, where we've added something or modified something. And then state F might be something where we've branched off to go and attempt to make a new uh, feature or a bug fix or something like that. But state F and state C both have the same parent as state B. So state F, its changes are based on whatever the state of state B was, and then we've added new things. State C is also based off of whatever those changes are, but we've added something different. So that's how this works. We have states, and within the graph, we have this directional property here. So state I, its parents are states G and H in this case. And that means that it has the merged states of those two nodes put together. So it's been merged together in some way. And how it's been merged has been done in a particular way to ameliorate any conflicts. But the idea there is that people are going to be working on these different states and then wanting to combine their work together over time. Or it's just one person who's working on different experiments or different bug fixes or things of that sort. So it's key to remember that that's what you are looking at when you're looking at the current state of a Git repo. It is one of these nodes in this graph. And when we talk about things like detached heads or about uh, certain branches or certain states of branches, we're referring to references to these nodes. So anytime you're looking at the state of a repo, those files and everything you see in there essentially represents some node that you're pointing to currently at that point in time. And you can change what you're pointing to by doing checkout and moving that pointer around. We're going to not do really any of that today because that gets very complex. And for your project, as I say, it's much less relevant. But it's key to remember this is here. So you can create a new repository with the git init command, and that will set up the current directory with a .git subdirectory. And then that will be something that you can then start adding files to and do changes and start tracking those changes over time. We're going to do that very shortly, but it's key to know that quite often what you're going to do is create a new repository on a site like GitHub, which is a hosting repository server for repositories. And then you'll do with that is then clone that locally. So it's very rare for you to actually create a new Git repo just locally and then do something with that and then push that somewhere. Quite often you'll create a repository on a server like GitHub or any of the others are like that, and then pull that down to your local computer using a clone command. And we'll talk about that very briefly. So remote repositories like on GitHub or GitLab or Bitbucket and other places like that, they represent a place where things are stored on a server, and then the Git command will interact with that server over HTTP commands. So you'll go and you'll contact that server and then pull all of the changes down and populate that .git directory with all those changes that that server stores. So the git clone command will start that process where it will pull down a new directory, set up all of the actual links so that the git command can be used in the future to contact a directory and know which directory that is. So this is what's going to go on with this. And quite often, this is, as I say, what you'll be doing. So starting from scratch is very rare. And then whatever changes you do, on your local clone for this, those will be pushed up to that server using the git push command. So this is quite often what the process that you'll want to follow instead of doing everything locally. So you can actually do this yourself. If you have Git installed, you can clone the repository for these slides. If you have just Git installed and you haven't actually logged into GitHub or have a GitHub account or set up everything for Git to use GitHub, then you can just do the first clone here where you're going to use HTTPS to pull it down. And then that will create a copy of my repository on your local computer. And if you had the right permissions, you could also make changes and push to it, but you don't because I haven't given them to you. So don't worry about that, but you can certainly bring it down and make changes locally. You and make branches and do everything else you like with that repository. So that option is there for you. If you have GitHub set up for yourself, you do need to have credentials to be able to do a clone using SSH, which is what the second command is. So whenever you see git at github.com and so forth, that's referring to cloning with SSH credentials, and that's a much more secure way of doing it. And you'll need to set that up for yourself if you're going to be doing committing to GitHub in a secure way. So the GitHub documentation is what you should be looking at to figure out how to do that. It's a bit of an involved process that is to do with how to use SSH and keys, but it is there and it's something that you can follow in their tutorials. So for this workshop, as I said, you'll probably want to make a GitHub account and then go through that process of checking or cloning something locally and then going from there. So the link to follow is this docs.github.com, and the Get Started page is very much that. It will get you started from the very beginning. And the tutorials, just follow them along and you'll be good. For now, what we'll do is go through how to use Git locally. So we're going to use these Jupyter slides, and the cells in these slides have commands that are run within the bash shell. So make dir git init. These are all commands that you can type in yourself locally in a shell. These are all going to be Linux commands that are assuming that you're running in bash. So if you're on Windows, you can use the bash program that comes with the git Windows install and follow along with this if you like. But this shows you what the output is. So what we're going to do to create our own local repository is use the make dir command to create a local directory called local repo. Within that directory, we're going to call git init, and we're going to create a new branch called main. So here we have this -b main command or argument to the command, and this will create a new branch called main. And then local repo is a directory we'll do that for. And then if I do just an ls in that directory, just to get a listing of what things are in there, we have the .git subdirectory that's been created for us and been initialized with the correct information. So that is there. And from that, we can then start doing things with that. As I mentioned, the double %bash just makes that cell a magic cell for running bash commands. You also sometimes see exclamation before commands, and that's for running bash as well. So this is a Jupyter feature. If you're not familiar with Jupyter, I'm afraid I'll have to direct you to the tutorials on that later on. But suffice to say, this allows us to create these cells and then these slides from those cells, which will contain commands we can actually run. So if you start Jupyter and go through these notes, you can run the commands as you go, and that is your actual walkthrough tutorial. So what we're going to do now is just change our current directory into that new repo that we just created. This will just make commands a lot easier for us later on. So thinking about, we are now in this directory. We're now going to be working with what we're doing internally for our repository. We want to now create a file and then show what that looks like in terms of what Git thinks is happening with that file. So don't worry about what these weird bash things are doing, but we're going to create a file that has these 3 lines. So A equals 1, B equals 2, C equals 3. That's it. This is a valid Python program, but never mind. We're just going to put this into a file called test.txt. And then we ask Git what it thinks that is. So the git status command will tell us what the current state of the repo is. There's nothing been committed yet. It does tell us that this file is not tracked. So we have to explicitly add a file into the repository for Git to start tracking it. It's not just enough to create the file in that directory. It has to be explicitly added. And it tells us right off the bat to do that with git add. I'll note that Git will sometimes suggest commands down here whenever something is maybe not working or something is not added yet. I wouldn't always trust what it suggests, so just be aware. Just understand what you're doing. But for this is definitely correct. We're going to add this file to our repositories with the git add command. So that just adds that. And then when we go to commit, which is going to tell the Git system that we want to make a snapshot, essentially. We want to create one of those nodes in our graph. And then that state is going to be kept as essentially that snapshot in time of whatever all the files in our repository are. So what we'll do here is we add our test.txt file and then we commit and we add a message for what our commit is. And the message is always very important to explain what your commit does, what it represents. So all we're doing here is just adding text.txt, and then that's going to be the final state of our repo. So if we look at what our log is, we see that this commit was made. So that created that new node in our graph structure that contains the changes we did to test.txt, and which is just creating the file from nothingness. And then we have our message down here. The log would be far more important once you do more and more commits, because every time you do a commit, of course, you're going to add a new node to your graph. And then that commit, of course, has a parent node and so on and so forth. And so the log can become quite complex, but it does keep track of all the history leading up to where you are. I realize people are raising their hands. I'm going to skip through the slides first, and then we can answer questions afterwards, whichever haven't been answered yet. What I want to show you now, though, is if we change our file and then see what Git thinks of that. So if we change the last line to be 3333 instead of just 3, and then we run the git diff command, this will show us the difference between whatever the current state as stored in our graph is versus what the current state of the files is. So the diff in this case is showing us that the line C equals 3 was removed and replaced by the line C equals 3333, which is correct. This is what we did. We replaced our file entirely, but the first 2 lines are unchanged. And so it knows that that is the case and that this is the actual difference. This is the actual delta of whatever is in the committed repository versus the current state of the files. So Git thinks that C should be 3, and we're saying that this is now changed to be this other thing. So with our change, we can then add this if we want, and then create a new node that will track that change we made to our file. So what we'll do here is call the git add command. This will add the changes into our new commit that we're going to want to create. And then when we run git commit, that will then create that commit, take all the files that we've changed. If we've done add multiple times, this will keep all those files together. And then take all of that, put that into a new node, and add that to our graph. And then once more, if we look at our git log, we can see that we have then this new commit up here. And what we're saying here with this head pointing to main is that the current state of our system, of our repo, is head, and that points to this commit right here. So the current state is that node in that graph. That's what this is saying. So talking about branches, as I mentioned earlier, this is very important. This is a very useful and necessary tool for collaborative development in software systems. It's also important for you personally, just even on individual level, if you want to try experimenting with different changes and you don't want to change a file and then overwrite things or comment parts out and then leave them commented. You can instead make a branch, modify things, see how that works, and then your main branch or whatever other branch represents the real state of your system or the best state of your system remains unchanged. But branching is something that can be quite complex because when you do make branches and then you want to amalgamate the changes from that branch into some other branch, often conflicts come up. Often there's issues with how the graph is going to get restructured, and there's different ways of doing mergings as well too, which change how the graph gets restructured, and then also changes in terms of what this is going to look like in the final system that you're putting together. And when you're just changing the contents of files, it can be relatively straightforward. But when you're moving files and deleting files and doing other more complex things, it can become quite confusing. Git does its best to try and figure out what's going on, but it's not always perfect. And so you're going to have to deal with conflicts manually quite often. So if you look at what's going on with this command here, what we're going to do is call git branch and then just give a new name for our branch. So we'll call this new branch here, just very straightforward. And then the git checkout command will then change what we're looking at in our repository to point to whatever that new branch is. It'll be unchanged for us at the moment, and so nothing will appear to be changed, but this will actually now change what the pointer for head is essentially to point to that new node in our graph. So what we're looking at, the files we have in our directory are going to be represented by that node that we're pointing to now. So we now have that split in that graph where things have diverged. We can now make changes to our file. So we'll just change this now to b equals 2222. So this is now a change that we're going to commit. And we can just do this very quickly with the git commit command. And we'll say -a just to automatically add things we've changed as well. So this will add this file for us. And we just say that some message about what we're changing for this file. Now, the next command that's very useful, well, if we go back to main here, and then what we are going to then see when we check out main is the state of that file is going to be what we left it as. So that change we just did in our branch will not be reflected here. If we add a new line to this file, which we do by just adding d equals 4 to the very end of it, this now represents a change that is different from the branch and also different from the parent node that both main and our new branch came from. So we now have big divergences here. There's new states that these nodes represent that are very different. And then we are going to commit that and then look at what the log says for that. So if we look at log and we ask it the graph for us, what we have here is a graphical representation of these different commits. So the commit 334, so forth, that was what the initial parent was. That was when we had just the ABC lines. We then create a new branch which diverged from that and then made changes to test.txt in that. We then went back to our main branch and made further changes that were different again. So we now have these 4 different states of our system. And the main, which is pointed to by head currently, and the new branch, their states represent whatever they've done on top of the previous 2 branches. So now we have these different branches. We can continue making changes and modifying things to them separately. And we know that those states will be kept separate so long as we want them to be until we want to do a merge. So that's the basics of what goes on with that. If we look at doing an actual merge, this is going to be straightforward here because there are no conflicts. But what we'll do is then create a new commit that's going to amalgamate those changes from those 2 branches and try and add those things together in the files that are changed. So long as Git can figure out how to merge them, it will go ahead and do so. But whenever there's a conflict that's very hard for it to try and ameliorate, you're going to have to do that manually yourself. But as I say here, it's very straightforward, and we get a very simple graph structure like this, where we have diverged and then we've converged back again into our new commit, EE0, so forth. And then that is our state of our system. That is the amalgamation of all those different histories put together. So as I mentioned, we were able to do this very easily because there weren't any conflicts, but dealing with conflicts can be quite complex. Websites like GitHub, which will host your repositories, can help you with that conflict resolution quite a lot. So it's very useful to use things like GitHub, and other collaborative things that GitHub provides are very important as well. For your projects, you're probably going to stick to one branch and you don't have to worry about all this, but it's just very important to be aware that that's what's going on. There are a lot of concepts which I have not covered here. I'm trying to get through a lot of the topics that are relevant to you now first, and then we can talk about anything else that is that you see that is important that you want to get clarified later on. But thinking about other concepts here that you'll see, or other issues that you'll see crop up, one of the things is a detached head state, which is where whatever the head is of your system is pointing to some commit that isn't just the tip of some branch anywhere. So it's going to be, you're pointing to somewhere within your graph rather than the very edges or the leaves of your graph. That's what detached head means. Uh, we mention detached head a lot, not because it's common, but because it's just very badly named. And whenever it happens, people don't know how to fix it. So uh, whenever you do have that issue, it's very worthwhile just to check out a branch once again, just to get back to wherever you were. Rebasing is a way of rejigging your graph instead of merging. We won't go into that. Again, there's other components to how Git repository is configured, and things like remote URLs are certainly there. So when you clone from GitHub, the remote URLs will be set to point to wherever that clone lives, but you can have more than one. And there's different reasons why you'd want to do that, to pull information from different repository storage locations at once. Things like tags, cherry picking, and other nuanced Git commands. I'm afraid I'll have to leave that to the tutorials on Git for you to see. Pull requests or merge requests, again, are ways of doing merging, but those are collaborative tools GitHub and other websites provide to you, but they are very powerful. So they're definitely worth looking into. GitHub is not just Git, it is a lot of other features on top of that for project management. So I would like to, instead of taking questions now, move on to Docker, and then we can come back to anything that are dangling references you want to talk to later on. So Docker, as I mentioned earlier, is a system for putting together a containerized application, essentially. So a container, or an image in a sense, is going to be essentially a Linux configuration, a Linux system that's been set up in a way with install commands and with files being copied over, such that that can then run almost as a self-contained operating system. So Docker and other containerized environments, we use the host kernel and operating system to run, and that's different from a virtual OS, which is going to run in a virtual machine. It thinks it is the whole system, it thinks it's communicating directly with hardware, which is a lie, but that's what a virtualized system is. With Docker, the system is going to run more or less as if that were the case, but it needs to explicitly use the host to do kernel operations. So, you can't change what version of Linux you're running, but you can change virtually everything else. There are other technologies like Aptainer and Podman. These are out there and they do very similar things. So the package systems that you'll be using, we'll talk about this very briefly, but it's very much the same sort of thing you'd use for setting up a Linux system. And then there'll be other ways of deploying these as well too, but we're going to be sticking to the command line for today. So often these things are used for packaging systems for deploy. So for our cases, this is going to be putting something together for deploying machine learning algorithms. It could be instead for deploying uh, server systems, for deploying databases and other things of that sort. So the advantage here, though, of course, is going to create a package that is going to have everything in it. So all the libraries you need, all of the setup that you need, all of the dependencies are all going to be put there. And then you can just take that image and then run that anywhere. And assuming that that Docker is set up correctly and that the OS is providing you the same facilities, that is virtually guaranteed to run everywhere. And that's the key thing, is be able to just take something together, put it into one big package, and then deploy it all over the place. For giant server systems, this makes a lot of sense. For you, this makes sense because this is very useful for reproducibility. You can give that Docker image to somebody else, and you're practically guaranteed that they can run it, rather than having to give them instructions for installation and setup and all sorts of other things. So all that installation stuff you do once and then run it many, many times. So an image represents what that package system is. When you run that system, that is a container, that is essentially the running application. And then that is something that will have a certain lifetime and then stop. And that will be separate from your actual host operating system. Images are often stored in registries, which are going to be local registries that are databases or other registries that are remote, like Docker Hub. And those places are where, when you run things with Docker, they will be pulled from. So you can also stick Docker images into archives, but that's usually not done that way. Typically, people will use repository or registries to store things, and those registries might be remote and not local. But whenever you want to deploy something, you usually push your image to a registry, and then that is pulled by whatever the deployment system is. But that's getting quite complex now. We don't need to worry about. So the key thing is that the images are going to store the file system for that system as you've set it up. And so the setup that you do is about configuring that file system and then packing it together. So we can invoke Docker here very easily on the command line. I'm just going to go to the parent directory, and then using the Docker run command, we're going to run an image into our container called cowsay. And what cowsay does is just print this ASCII art that says whatever you wanted it to. So what will happen here is Docker will go out and find this image called cowsay that's been provided by this user called, sorry, whatever that was. Sorry, we have backed up a little bit too far. Sorry. So as I said, this was the user GuiCap. They have put up something tagged as cowsay, and this is just going to be a program that is encapsulated in a running system that just has this command called cowsay in it. It does this, and that is all that does. And what Docker will do is, if it doesn't have this image in a local registry, it will go out somewhere and try and find it. So in this case, it will have gone out to Docker Hub to try and find what this is. So it, by default, my system is set up to log into Docker Hub, and then it will go out and find whatever this is. And this is a public image, so not all things on Docker Hub are public, but this is, and so Docker can go out and find it. This is a bit of a busy slide, sorry about that. But containers, they don't necessarily clean themselves up when they're done running. So as you see here, if we run Docker container ls, we can see what things we're running. Everything here is exited, but when you do want to run things in the background, this is something that Docker would do for you. So you can start a container, and then it can continue running in the background. Especially if you're running a server, you want that to run indefinitely. And so that will be there for you, and it will continue as a background process essentially. And then this ls command here will show you what background processes are running. We can also see what images we have. So as I mentioned, the images are the packaged environments. We have a bunch of images here. At the very bottom is the one we just ran. We can see the sizes. Some of these get gigantic. That's just a Docker thing you have to deal with. There's a number of other images here that are related to the tutorial information that's in the repository for these lectures. So these are things you can create for yourself as well too, and these aren't terribly large. So these are the things we can run if we want to. So the way that we create a new image is almost always with a Docker file, and the Docker file contains essentially a bunch of commands, and these are for copying data around or for running commands within that running environment to set up that file system the way you want it, and then package that up into the final output. So we can go over these commands very briefly, but it's relatively straightforward in a very simple case. You're going to copy files from the host, which is your operating system, your environment that you're running in, into the actual image itself, and that's what copy represents. And then run is about running commands like doing installations, doing downloads, and other things that will bring stuff into the image and then install dependencies and set things up the way you want. So we can look at a very, very simple Docker file here. What we're saying with the from command is we're going to start by start by using this image as our basis. So we're going to start running as if this were the image that we had already set up. So this will go out to Docker Hub and pull down this image. This just contains Python version 3.12 and very little besides. That's what the slim means. So the 3.12-slim is the tag, and this is just a particular version of this image that has been provided to us by the by python.org. And we can just start from that and then configure that image the way we want it. So the next thing we'll do is just run pip, and we'll install the cowsay image or cowsay module that is a Python version of the cowsay program we just saw. So we'll do the very same thing. It will write out just something that's going to be an ASCII art image of a cow that says something in a text bubble. So this pip command is the same pip command you use for doing any other setup that you want for installing any other dependencies that you have for your program. Workdir will set the current working directory to be /app. And then what we're going to do is copy a file called myapp into /app. And then command is going to say that whenever we run this as just a program without any other special arguments, the default thing to do is to run Python and then myapp.py, just the single argument to that Python call. So that just sets up what is the default sort of entry point for your Dockerfile program. This goes through everything I just talked about here. Command is what I use here. There is another thing called entry point. They do vary a little bit, but I refer to you to the Docker instructions for that, but I would just stick with command for now. There is a few other commands that are important, but these are the ones that you'll see most often. There'll be things for setting environment variables or for arguments, but almost always what you'll see are these commands as being the key things for setting up your environment. So we're going to write out our little myapp.py file here. It's just going to import cowsay and then say the very same thing again. So this is the entirety of our program, just 2 lines. Yours are going to be more complex, I do hope. Once we have that together, we can then build our new image. So we're going to call Docker build. The -q is just to keep it quiet. And we're going to run within the current directory. And that will by default look for the file called Docker file. So I don't have to specify explicitly with -f. And then -t is going to tag. So that's going to set the tag to be cowsaypy for the new image we're going to create. And then once we do that, we can then run this program of ours. I added -rm just to delete the container once it was done. But what's going to happen here is we're going to run our cowsaypy. Docker is going to look and see in our local registry that we have this image with this tag, and then just run that directly. And it's going to do the exact same thing. So it's not very different, but this is actually going to be the image we just created that's going to get run here. We can do things a little bit differently. Here we can, instead of just relying on what the command configuration said in Dockerfile, we can instead bring up a terminal or other programs internally. So what we can do here is with Docker run, what we can do, it's particularly here that's going to be relevant to you, is mount a directory in the host within the running container. So typically whenever you run Docker, remember the file system you have in that running environment is going to be what you configured. And if you want to communicate with that, typically what you do is mount a directory in your host within that running container. So what we're going to do is mount the current working directory. So that's going to be in this case, the repository directory for these notes. And then we're going to mount that in a place within Docker, within the running container called /curdir. And then we can interact with that, with whatever is in within that directory. So we can modify files, add new files in. So if you want to read files in and then produce an output that you then keep once the container exits, this is the way to do that, because when the container does exit, it loses whatever changes have happened while it ran. So the image will not be modified when it stops. So you lose any files you create if you don't put them someplace else. So this is one way of doing that. As I showed earlier very quickly, you can add -ti to create a terminal, and then you can run a bash within your running container and actually have an interactive environment if you want that as well too. So we can go through all that, but that is something that's also talked about very in depth in the actual Docker tutorials themselves. So For more in-depth information, I'm definitely going to point you towards their own tutorials, and they're linked in the repository of mine as well too. You can output, as I said, an image using Docker save. This will produce for you just the binary output for that image, which is essentially just the file system itself. And so we can save this to a compressed tarball with this command here. This is, as I said, not very common. So typically you'd use a registry of some sort and push it to a registry. So the local one is the default. We can also push something to Docker Hub explicitly. You can create other registries as well. You can run your own registry server locally if you like, and then push to that. There are other registries that are out there. NVIDIA provides their own registries, for example, for NVIDIA images, for running CUDA and other deep learning related things. And there's many other options out there. So you can log into other registries however you like. And you can have images that are public or private on those registries, depending upon what your plan is or what the configuration of that system is. So images are often used together. They often collaborate using orchestration tools like Docker Compose. We will not get into that at all. But the key thing with a lot of that orchestration is to reuse existing images and not create new things. So trying not to reinvent the wheel over and over is a key thing to Docker, because that very much helps you reuse existing setups, not have to build your own new things. So there's many other things I have not covered. As I said, the key things about how to set up your container to use GPU resources. So it's set up with CUDA in particular. So it's how to use PyTorch and other things. There are a number of ways of doing it. In the repository for this repo, there are a number of examples of how to actually set up your own environment. So how to set up things to use PyTorch with CUDA acceleration. There's Docker files for how to do that will produce relatively small versions. You can also pull Docker images from NVIDIA, which have everything pre-set up for you. And those will have environments for compiling and also for just running things like PyTorch programs for training or for inference. Those will all be there. So definitely go look and see what is available out there. Beyond that, there's many other concepts I certainly have not covered. So layers in your Docker file, how to do things with Compose or other orchestrations, and other frameworks such as Aptainer, which do very similar things but have their own nuanced differences. So I won't go into those, but looking at the example files that I provide in the repo should be the key things to picking up enough information for this week's summer school. So that was very much the whirlwind tour of these two technologies. So I hope that is going to be helpful for you. So thank you very much. And now we have plenty of time for questions. So Alvaro.
Yes, Eric. We have three different questions. So the first one is, can you explain how to use Git effectively inside the Visual Studio Code?
So in VC Code, there is a plugin for Git, and that really is a key thing to be using. So what I've shown you everywhere here has been the command line, because that really is what you need to understand how to use, just in case you're in a place where GUI programs fail you. So you really need to know how to fix things with the command line, because sometimes you'll just have to do that, because Git lets you it'll let you shoot yourself in the foot very easily. So I'm going to stop sharing screen for a split second here so that I can bring up a Visual Studio example for everyone to see. So then if I come back to share, and I will share here. Share. Okay, you should be able to see Visual Studio. The text is
Yes.
very small, I'm afraid. Let me see if I can zoom in more easily here for everyone. Yes. So this is Monai code. I'm working on a Monai branch right now to try and fix something. So don't worry about exactly what's going on here, but I have the source control plugin installed. And so we can see here the name of my repo. This is a clone, but don't worry about that. We have information about what my current branch is. Uh, this is a file I changed and have not committed yet. So we can actually, if I click on that, it actually shows you the delta between what is currently on the repo and what my changes are. So you can see I deleted a bunch of lines. That's what that shows. That's it. what we also see here is also useful as a visualization of what my current branch is. So I'm trying to get PyTorch 2.7 to work with Monai right now. That's what I'm doing. I've merged in whatever the current state of the repo is here, and you can see all the different changes that happened there, various little branches that happened, and it's pretty quiet here because this is mostly from just a fork. But if there's many people working on a repository, this can get very messy very quickly. But this is the graph. This is what I showed you earlier in that picture. These are the different commits, the branchings you can see here and the mergings you can see here. And you can click on these and they'll show you what the actual changes in each of these represent. So if I click on this one, these two files were changed by this commit, and then I can click on this. And once again, it shows you here what those changes are. So this line was just added and that was it. So this is here. This will show you how to do things. The commands for up here, so I can add this to a commit, and then I can type in my commit message and then hit the commit button, and that will then put my changes into my graph. And then I can also push that to the remote here too. And I can do things like checking out other branches, and many other commands are here too, and create tags and do all sorts of other things. So it's here. There's a lot here. It's going to be a bit overwhelming, I know, but a bit of tutorials on this are available as well too. But this is just going to be the Git graph and other plugins that are available here. So in the marketplace is a number of ones: Git graph, Git history. Some of these are third party and very useful. I haven't used this one, but it's worth looking into. But there is the default one for Git that comes for Visual Studio that you should get, and then that will allow you to manipulate these repos in this way, and that integrates everything else together. Hope that answers that, but I need a few more hours to go through Visual Studio with everyone.
Yeah, I think it's very clear, at least the plugin for GitHub in Visual Studio. Another question that we have here is in a cluster or in Slurm, which mode the Docker or Aptainer Singularity is preferred?
So it depends what your setup is on that system. With Slurm, because what a Slurm script is just a bash script, right? So you can run whatever you like inside of that. So whatever your system is set up for, if you're using Docker, you do have to be aware of mounting directories so you can get your outputs out again, of course. So if you get data in, you need to get your results out. So you need to do that. Aptainer is very much like Docker, but the difference is that it overlays the file system with a host in a different way. So your home directory is actually the same within a running Aptainer container, whereas it's not in Docker. And within Docker, you run as root typically, whereas with Aptainer, you're going to run as yourself. So permissional things are very different. And so for those reasons, Aptainer is just easier to use in a system like an HPC that's using Slurm for job control. So if you can use Aptainer, I suggest doing that. You can create Aptainer images from Docker images or from Docker files. So everything I was showing you here, you can actually use with Aptainer as well, and that's kind of the easy route to using it. And I would hope your HPC would have lots of pre-made containers for you as well to use, but I would recommend looking into Aptainer. But once again, that is a big ball of wax.
Then another question, that this one I think is more specific to a repository or a project. You mentioned that we use an open source GitHub and then we want to clone it in the collab, but we want to run it with their own data sets, which make us some changes in the utils of the PI. I find these things by asking, but I don't know how should I learn the trick to make the changes. How you should learn those details.
I'm not quite sure I understand the question here. What the first part was, like you know, they're using something on GitHub. They're using GitHub repo, yes?
I think they're using a GitHub repo or a specific project, and they want to use their own data set within this repository.
Yes. Okay. Once again, I'm going to swap to a browser and just show you one thing on Git that is quite important. So here we are in a browser window. This is this is the repo for these slides. So one of the things that you can do in GitHub is create a fork. So what this will be is a clone of this repository that's yours. So it's your own personal repository now. I can't fork it because I own this. But normally you can create your own fork, and then that is essentially your copy of that. And then you can sync up your fork with the original too if you want in the future. But that's the way to do that, I think. You create a fork and then you modify it however you like. And then you can commit that information, and then that will be on GitHub under your account. It won't be changing someone else's code or whatever else. All of you can fork this my repo now if you like. You can go ahead and do that and play around with that. That's perfectly harmless. And then if you want to actually merge some of the things you've done back into the parent, you can do that through a pull request, a PR. And that's how we do Monai development. So if I go to Monai, here's the main repo for Project Monai. Under the forks, I can click here to go to my fork. And this is what I was showing you, what I was just doing in Visual Studio. So I was making my changes here in my fork. And then when that change is ready, on the main repo here, there'll be a thing where I can create a pull request from that branch in my fork, and then it will bring all that data over and then merge all those changes into the main one if it's approved, because we have rules for approval and everything. So if I go to PRs and I come down to what I was just working on, so you can see here, I want to merge my 16 commits from this branch in my repo into the main one here. And then it shows me what files have changed and so on and so forth. So that's what a PR is. It's about, I want to do this changes, I want to add these things in. Someone please look at it and approve it, or tell me I'm doing something silly or blah blah blah. Let's have the conversation about doing this. And anyone can do that. Anyone can propose a PR into Monai or any other place. But the useful tool here is to do that from a fork, because that's your own private copy that you can do what you like in. So I think that answers what they're wanting. I think so.
I think so. Then we have a couple of more questions. I think this one is more related to your dev setup, in which you have an SSH workstation. I guess you are coding from a server or a remote session.
Right. So in Visual Studio, what I was doing was connecting to a remote server through its SSH plugin. So that's kind of unrelated to everything we talked about, because when you are connected through the SSH plugin to a remote system, you have command line access, and also you're running essentially a VS Code server over there. And so the plugins like the Git plugin will look at the information over there on that server rather than locally. So that's a separate issue in entirely. I think, but that is a very useful tool as well too. Once again, I don't have the hours to go through what VS Code can do for you, but there's a lot of things that come together in VS Code that will make your life a lot easier. But as I said, certainly with Git, understanding the concepts first, so that when the tools tell you something weird, you understand what's going on and can fix it, or understand what you did wrong. Because when it does get confused, it does sometimes fail, and it will just tell you a Git output that can be very cryptic. So as I say, understand what's going on first, manipulate the things on the command line first, understand what they do, and then that experience, because it really is about experience, will help you going forward.
Then another question from Hassan. Is it important to have deep details in Docker and Git, or we just cover the main concept? So I guess, what are the most important features that you can consider to learn in Git and in Docker?
So I think I covered them. I think, as I said, those things about creating commits, pushing those, and then keeping track of your history over time, that is the key thing that Git is going to provide you. So again, coming back to the repo for these slides, I can click here on the history, and there's our 6 commits. So that's showing you what's going on. There's no branches or anything, of course. So those are the very simple things that Git can do for you. So if you're just working on your own, that can be quite straightforward. When you start collaborating with other developers, that's when it gets hairy. And then those things will still be there, but there'll be a few other things you need to learn on top of that, like how to do merging. A lot of that GitHub, of course, helps you. VS Code helps you, so you don't need to see those things too much. For Docker, it's the same story. I think I've gone over really what are the basic concepts here, and there's going to be some fine points that I've not gone over, but this is why I've done things as a Jupyter notebook, so you can go through stuff and experiment and play with it yourself, and then figure out the nuances. Here in Docker file examples, I have a number of examples of simple things in Docker files and how to actually build and then run them. So these will go over a number of concepts. So our calsay one is here. This one is for doing input and output. So just running a program on inputs and producing some outputs, just see what that looks like in terms of mounted directories. Minimum Docker file for using PyTorch. So this might be, I think, something people will find very useful if they're using PyTorch. This will set up a system to use CUDA and everything else, without any of the bells and whistles, bare minimum, but it runs PyTorch, and that's probably all you need. So definitely look at that file. For something a bit more involved, I have a second repo that I put up here for a Monai classifier. And going to that, this is Monai 101. This is files based off of the Monai 101 tutorial in our tutorials repo for Project Monai, but this goes through a training script and an inference script and how to put a Docker file together for doing inference. So you can create a directory with images, because this is a classifier. You can mount that directory, and then this Docker file here will represent a program to look at the images in that directory and then try and predict what those images are for you. So this is a full soup to nuts system of training a classifier and then putting it into a deployed configuration with Docker. So I think this is very useful to look at. This is very similar to what the other Docker files are like, but if I come back to that, I know I'm jumping around, sorry, but if I come back to this, very simple commands. We're not doing very much here. Starting from Python Slim, we're going to create an app directory and then copy everything in our repository into it, and then just do an installation that uses our requirements file. And our requirements file is just going to include Monai and then a few other secondary dependencies of it. But that will set up PyTorch for you. It will set up NumPy. It will set up everything else that you need, because you already have the Python set up in that image, because we pulled that down from the parent image. So that really is it for using Monai. We also have a Monai image, but it's 25 gigabytes. So it's huge. It has everything and the kitchen sink thrown into it. So it's up to you what you want. If you want bare bones, this is really the way to go. Another thing I was working on was a Monai Slim image, so I'll get to that at some point in the future. But it's looking at examples, looking at other people's Docker files. Virtually everyone will start from someone else's Docker file and tweak it to their taste. That's just the way forward for that kind of thing, because you don't need to reinvent the wheel.
It's good. And I think we have last question regarding the previous one with the fork. So if we fork the repo, then apply some changes, then clone it, it will work after that changes.
Yeah, so when you clone, you're going to be explicitly cloning the repo that you want. So your fork is just another repo in this case. GitHub keeps track of some relationships with the parent, but it's just a new repo. So let me see here if we want to go back to Visual Studio. Let me just once more share a different screen. So if I do make it a bit larger, if I do git config local list, we get a bunch of things that aren't relevant. These are for branches, but one of the key things is about the origin URL for my repo, and it's just this. So this would be the same for any other repo of mine. It just happens to be called Monai, and this is my fork of the Monai repo that I work from. We have information here about the upstream one, which is Project Monai, the actual real repo. And this information is here that you have to set up to be able to do changes. But the key thing here is that this is cloned this way. If I back up and look at what's in this directory, I have many other things, but I have also the actual Monai repo itself. So if I look at this one, this is also going to be a bit of a mess. But here the origin is just Project Monai. So I have two repos, two checkouts that are two different places They store very similar information, but the relationship between them, the fact that one's a fork of another, is just something GitHub keeps track of rather than Git. So there are a lot of concepts that are built on top of Git that aren't strictly Git itself, like forks. That really is a GitHub thing. But you can just make a fork and then check it out separately. And as I've shown here, Monai versus Monai mine and the various other different things I've checked out, just different directory names. And that way you can have checkouts of both and just have them side by side and do what you like with them. And that really is the developmental process that makes sense.
Perfect, Eric. So thank you so much. There are no more questions. I think it was very, very
Cool.
clear.
So yeah, if you have any other questions or any other feedback on the repository for these slides, you can raise issues. And so those will be things that we usually use for like feature requests or bug fixes or things. But if you have any other feedback, you can put an issue there or ask any other questions, and I'll try and keep track. GitHub will probably email me if you put anything up there and tell me about it. So that's the way to get back to me. Otherwise, you can find me, of course, on KCL email or on LinkedIn. Cool.
Perfect. Thank you so much, Eric. So I will conclude this session and we can start the break.
Cool. Thank you.
Don't like it. And maybe I should respond.
Can you see?
Yeah, all looks good.
Okay, great. Should I get started then?
Yeah, I think we can.
Yeah, perfect. So, good afternoon or good morning or wherever you are in the world. Greetings for the day. So, I'm Carol Sud. I'm working at UCL at the Unit for Lifelong Health and Aging and the Hawkes Institute. And so this afternoon, for me, I will talk to you about uncertainty and uncertainty quantification. And this is the program that we have for the day. So I've decided to cut my lecture in 3 parts, and each time there will be a small tutorial or small hands-on activity associated with each of those. So the first part will be more of an introduction to what uncertainty is and why we need it, and how we have actually easy way to assess uncertainty in with statistical methods. Then I will go a bit more into some of the methods that we have when we have, in particular, deep learning methods to quantify uncertainty with typical strategies, how we measure it, and you will get to try out a few of those. We'll mostly focus on ensembling and test time augmentation in the practical. And finally, I will touch upon calibration and conformal predictions. What I'm aim at doing is having a small break in between those the things, probably in between the deep learning and uncertainty, or between each of those main themes, but probably shorter than the 30 minutes, so 10 minutes each time. And so we should finish 10 to 15 minutes earlier, hopefully, if I keep to time.
Carol, actually, I just realized I didn't introduce you. So maybe that was, I mean, I know you and I realized, oh, okay, we'll just continue. So maybe just before you continue, I can just, I don't know if you want to do, but I can also just, I have your brief, so maybe I can just tell everybody a bit about you.
Yeah, so I was just saying at the beginning, so I'm at UCL in these 2 units, and I'm an associate professor there. And just for you to know a bit, I'm quite interested in cerebrovascular disease and all the what relates to very small lesions in the brain related to vascular poor health. And so that's also why I'm quite interested in uncertainty, and I've actually helped organizing the intro workshop part of MICCAI satellite event for the last 7 or 8 years. I mean, I think we are doing the 7th edition this year. Yeah, so that's about me. But a first thing before we get started, and we'll try to see if it's easy for you to intervene and to put things in the chat. I'll try to ask a few questions to get you involved as much as I can. You should have also had a link to a Google folder where you have all the material for the tutorial today. Hopefully that's working, and you have the uncertainty RISE Jupyter notebook to help you out, and all 3 parts will be in that notebook. But before we get started in earnest, if people could put in the chat why they think uncertainty is important and why we may need it, especially in medical imaging related applications. I'll leave you roughly 1 minute to put your ideas in the chat, and then Taryn will read out a few. Yeah, we'll see.
Then sorry, Carol, I think Masa just has there's a few people putting their hands up, so maybe I can just quickly check. Masa, I'm not sure. I don't know if it's something to do with the link or Masa. Or maybe they'll message me. Okay.
Hands have been put down. Okay.
Yeah.
So I just repeat the question briefly. If you can just tell me why you think uncertainty quantification is important, and what we can use it for. Any thoughts from anyone?
Yeah.
Do we have
We have
anything
some.
coming?
Yeah, we do. One says to understand the difference in coverage assumption that may vary for each patient, increase model accuracy. The one says it's important to address how certain the models are, but its predictions, specifically in medical settings, how well it's performing. It's important because you could have some noisy labels to understand model confidence. So people, they talk about the inter-annotator heterogeneity.
Yeah.
Those kind of things.
Those are all excellent points, actually. Indeed, the generic use why we want it is because we want to know when we could be wrong, and that could be because we haven't seen those type of data before, because there is a domain shift, and actually our model is not performing as well, but we need to realize that something may be wrong and that there is potential for failure. We need to know the limits of prediction, because usually we get a point estimate, but actually what we're interested in is also the confidence interval around that point estimate, and because that may affect our course of action. So for instance, if you imagine something that is extremely confident and truly extremely confident in terms of clinical workflow, you may not need as many human checks behind than something that is very uncertain, and where the course of action for diagnosis or therapeutics may be different. That's also very useful when you need to just say, well, sorry, we can't use the result because it's indeed too uncertain. The confidence that we have is really too low, and so we can't do anything. And in terms of practical application, you can think of different diagnosis perspective. So thinking of whether, for instance, with certain typical phenotypic presentation, it's a migraine or a stroke that is presenting, or you could think of surgical planning where you need correct segmentation of organ at risks or of the tumor, and decide on the margin and know where to cut and where not to cut, and how it may impact the surgery itself. So those are just few examples, but you could definitely think of way more. And so here it's a typical what would typically happen in terms of diagnosis, where you have a clinician who collects some data, examines the patient, has the history, and they present with headache, for instance, and put all the data that they have into their AI system, and there is likelihood for a certain type of diagnosis to come out. And according to the type of diagnosis, so for instance, in the first case, it's extremely likely that it's migraine, so they will treat the migraine. In the second case, there is actually quite a large probability that it's something else than a migraine, and there is a possibility that actually it's an ischemic stroke, and in that case, there will probably be some further investigation of a cerebral vascular pathology, and that may, as you see, that affects a lot the type of either test that you do or clinical pathways that you follow. In terms of labeling, we mentioned it before. So here you have different input images, flare, T1 contrast enhanced, T2, T1 weighted. And you have a lot of different annotators that are supposed to be providing ground truth, but some of them may be wrong, some of them may be trained in different ways, some of them may actually, apply one label for the other, and then you end up with something a bit messy, like for the fourth one that is proposed here. And so you need to take that into account, just because you have different level of variability, you have different level of expertise, you have different training schools, you have different levels of awareness as well, according to how tired people are or how focused people are when they are doing the annotations. And especially knowing that it's this labeling often that is used for training. So if you get bad labeling, you probably won't get the trainings that you like. Another aspect that I want to mention is not related to labeling, but to another aspect of data quality, which is potential artifacts at acquisition. And here it was an example from a relatively recent paper where they looked at the impact of specific type of artifacts in terms of the acquisition on MRI and segmentation of the gray matter, and where you see very clearly that when there is some form of degradation of the image, obviously there is way more uncertainty, both in terms of the predicted probabilities and as well as the predicted uncertainty quantification. So I'm not sure you have heard about those two, but it's typically the two type of uncertainties that people consider. So people consider uncertainty to be divided roughly in two main groups. What correspond to aleatoric uncertainty, that come from alea, which means random, and that usually, as it says, come from the randomness. It cannot be tackled by more data. It just knows that is there and that you need to assess, but you cannot do much about it. And on the other side, you have the epistemic uncertainty, which is related to your lack of knowledge on the data. And that means generally how inadequate your model is. And so usually more data helps, and you model the epistemic uncertainty as the uncertainty over your model and your parameters. And when you look further into the aleatoric uncertainty, so the uncertainty related to the randomness in the data, you can have what we call homoscedastic uncertainty, when actually you have very similar uncertainty level at any single point of your input data. And you can have heteroscedastic one, where actually it varies according to the data. And so, for instance, on the edges of your distribution, you may have a lot more uncertainty than in the center of your distribution. And so I'm coming here to the first bit of practicals that you can do potentially, where we will look at ways of considering confidence intervals. And classically, confidence interval, when you have 95%, for instance, confidence interval, when you are looking at doing that through bootstrapping, where typically you take n samples in your data and you replace them. So randomly, they can be repeated, and you take n samples again and again and again. You calculate your statistic of interest, and then you calculate the 95 percentile confidence around that mean estimate. And so you can average across the multiple trials that you have done. You can calculate the variance and so the confidence interval. In the practical, it's a part one of the practical. And what you can do is in that one, we are using an emerge data, and so data from the from ADNI, Alzheimer's Disease Neuroimaging Initiative. And we are looking at hippocampal volume, if I'm correct. And we look at it according to how much of data we have each time. So looking at full data and then taking only 1 in 10 points or 1 in 50 points. So I will just stop sharing for a bit, check the chat, and then come back to you. But hopefully
It looks like no questions.
that's great. So I will let you go at it a tiny bit. I'll get my stuff ready, and then we can discuss the output, which should be it should be relatively straightforward for you to run it, and then we can discuss a tiny bit the output, which is that plot that I showed just before.
Carol, I think a lot of them, sorry, I was on mute. I think a lot of them didn't have that link, but I did send them the link on the chat, so it should be
Perfect. That's great. And so here what we are calculating is the hippocampus volume as proportion of the intracranial volume. So hopefully you will have seen that I go exactly about it as I say in terms of here how I do the bootstrapping, and then I plot the distributions of what I get for each sample of the sampling, and that's just to show you how actually sampling can help us in assessing uncertainty in our measurements. And what you see here is typically that you have a very narrow range when you use all the data, and it expands quite significantly when you have only 1 in 50 samples. And that tells you exactly what we were discussing before about the uncertainty and the amount of data and the potential issue with respect to your model, and the fact that additional data gives you more information when it's about the models that could be wrong. So typically that's what you see here with that confidence interval growing and growing and growing. Yeah. But typically with uncertainty, what we do is a lot of sampling. Sampling through different ways, but sampling nonetheless. So that's what I will talk about next. We'll talk about distribution sampling. So we'll talk about sampling from the distribution of the model parameters, sampling, estimating the variability based on different outputs if we have different inputs, and then trying to use the probabilities for risk assessment. And I just wanted to make a small digression towards Bayesian modeling, where actually it's kind of the basis of this idea about sampling and about looking at the distribution instead of the point estimate. So trying to consider the model parameters themselves as random variables, and where actually the data that you have can help you refine your idea about the parameter distribution. So again, the idea is that data can help you refine your model in terms of the epistemic uncertainty. And when you have data for trainings, then you can apply it for new data to try to either refine it further or try how uncertain your estimates are with respect to this new data that is being given. And that's what happens when you do Bayesian linear regression, where you start with some priors that can be very all over the place, as one can say. You have some lines that go down, some lines that go up, and then you have more data, and you refine your prediction to add something that is way more constrained in terms of your knowledge of the parameters. But each time you will have a distribution over each of your parameters, and that you can use to assess the uncertainty of your prediction estimates. And I really recommend that blog post. If you will see them in the note of the slides. It's actually very well done and very pedagogic with quite a lot of pictures and quite nice to explain. So really recommend it. So now we'll move on to the core of what we'll talk about today, so deep learning and uncertainty. And the first things that I will mention is that review paper from 2023, where they classified way of doing deep learning and looking at uncertainty in 4 different ways. Deterministic methods, Bayesian neural networks, ensemble methods, and test time data augmentation. So one could say that actually those 3 may relate more to the epistemic uncertainty, what relates to your model, and the uncertainty related to your model, while the test time data augmentation correspond a bit more to what we may understand as aleatoric uncertainty, while you will still see that you can do a bit of both in the Bayesian neural networks as well. Terry, I'm assuming that you follow the chat in case there are any major questions that come up and people want to discuss something urgently.
Yeah, I was actually trying to encourage them to maybe ask, because this is the part
Yeah,
where
it's very, very difficult. And I know it's difficult. It's difficult for you. It's difficult for me. I don't see your faces, which is terrible to teach. So I have no idea whether you get it or not. Usually when people start doing some weird faces, I know that something has gone wrong, but here I can't see you. So please don't hesitate to raise a hand or ask for clarification if something isn't clear.
I did, yeah. Oh, there we go. There's a question, as you said that. In slide 14, what's the difference in the method across in slide 14? Oh, she wants to know about the different categories, because you have A, B, and C, and D. So I think she just...
So A, B, C, D. So A is what we call deterministic method. We'll go a bit more in depth in those straight afterwards. But basically, A is deterministic method, where you just need one pass to have an assessment of the mean estimate and the variance around it. B is more about really looking at the distribution of the parameters, so trying to sample from the distribution of the parameters and then going through multiple inputs and then gathering everything as mean and variance. C, ensemble method, is looking at deterministic method, where you have typically one model that is on a deterministic way, and then you aggregate them, and from there you have multiple predictions for which you calculate a mean and a variation and a variance. And the last one, test time augmentation, you have a model that is deterministic, but you input multiple times slightly changed input, like you apply augmentation at test time and you get multiple samples on which you can again take the mean and the standard deviation. Yeah, clear? We'll go through it a bit. What we'll do is that in the tutorial, in the hands-on, you will see a bit what I've done in terms of ensembles and in terms of test time data augmentation, and we'll see the output in terms of the different measures of uncertainty.
Sorry, Carol, there's one more question.
Sure, please do.
It says, could you please share the underlying assumption and what could be the rationale to experiment across the, but I don't know if you're going to probably go into, why you want to use certain ones at certain points. Because she wants to kind of know which one's the rationale by utilizing each of those methods.
I may not go that much into the details of why one way may work better than another. However, what we can say here is, in the Bayesian neural networks kind of systems, you have a few ways to measure to have at the same time the aleatoric and epistemic uncertainty. The ensemble method is typically mostly the epistemic uncertainty. And the test time data augmentation is mostly the aleatoric uncertainty. So it's kind of those that may help. Then we can discuss a bit the advantages and inconvenience. It's often related to compute time, difficulty in training, type of problems, etc. So sometimes it's more a question of practicality. And you will see with the ensemble, to be honest, I've been preparing for that tutorial for quite a while just because I had to prepare quite a few networks. So in that case, it's quite heavy, it's quite memory consuming, etc. But once it's ready, and you can go at it and do whatever you like, which is nice. Some may have a bit more like Bayesian neural networks, sometimes are a bit trickier to train. It's also very much a application specific question. So it's often based on computational powers that you have, type of training that you do, and difficulty in getting things to converge properly. Sorry if it's not helpful enough.
There's more questions they come in. I think
Sure.
this will probably last one, but one person wanted to find out if there's a standard Bayesian neural network for deterministic models. That was the question, I guess. I don't know if anonymous.
I think so. Usually, deterministic methods is the ones that go in one go, and usually what they do. So I will just discuss that very briefly here. It's when they are actually aware of the distance, and especially on domain shift and out of distribution samples. So it's usually kind of models that allow you to model the distance based on the distance in features. And they are often based on some form of information theory, where they can have at the same time they use a modeling of a belief function over the probabilities of the output, and then you can extract the mean and variance from there. And I really encourage you to read those two papers if you want to know more about those deterministic solutions, that distance-aware networks or belief-based networks. And I have just one example from Gezo et al. Here on chest extra classification, where actually they demonstrated really that it was working well because they had predicted large predicted uncertainty for most of the cases for which they needed to flip the labels that was already assigned originally assigned. So they had some misclassification, again problem of label assignment, and after expert consensus some of them were flipped, and it happened that most of the flipped labels were on the components that had high uncertainty. So the advantage of the deterministic model is that usually it's just in one go and you don't need multiple paths or multiple samples. As I said, deterministic. And yes, please, Taryn, interrupt me whenever.
Okay, perfect. Yeah, I was about to because there was a Bayesian question, so I wasn't sure if I should let you first say Bayesian and then go.
Okay, yeah. So the Bayesian ones is usually when you're trying to get these ideas of this power distribution and trying to do something. Let me go through it, and then we see if there are further questions and if I can answer them. So typically, classically, when you do deep learning, when it's not the Bayesian, it's what we discussed before. You have a point estimate and that's it. And when you move to the slightly more Bayesian side of things, it's more looking at the distribution and trying to sample from those distribution. So you sample from the multiple times from the distribution of parameters, and you try to see what's the output based on those different samples that you get for every single parameters. And typically what starts as just a point estimate, where you know exactly what the weight is, comes back to, can we sample something from that distribution of weights and biases? And then you sample multiple times and you get your outcome. And one approximation of that is to do with a dropout, where actually you decide to nullify some nodes in your network with a certain probability, and from there you can get multiple, obviously multiple outputs, because you run it multiple times at test time with different, still with a dropout probability on, and you aggregate your outputs to get mean and the standard deviation of your outputs. And typically that's how you calculate it. So with MC dropout, so you do T or N stochastic forward passes, and then you do your result averaging, and here's how you calculate your variance based on that. And the P here is the probability of a node not being dropped in your dropout. And that's probably one of the most used methods for a Bayesian approximation for model uncertainty. And people have extended further that to have actually a further head trying to assess what the variance, the prediction of the variance due to the randomness in the data, so that you end up with a component that is more on the aleatoric part and a component more on the epistemic part of the estimation. Any further question from there? Because
Yeah,
now we move, yeah.
they were talking specifically to the priors. So I guess with
Yeah.
the base prior, the question there is that it can be quite difficult in general to set it up. So they're asking if maybe, maybe a view, but also if there's any kind of resources or any papers that you advise in terms of what's kind of the best way.
Yeah. So actually the paper that I like best is the first paper on Bayesian deep learning, the neural network, where it's in the slide as well, if I remember correctly. Oh. No, sorry, I don't manage to. So normally if there is a need, I will get you back the specific papers that are useful for that, but there is one of the first paper on Bayesian neural network I find quite useful in terms of which type of distribution to choose. Usually a Gaussian distribution is good enough because it's actually quite flexible. You could potentially go still to the Gaussian related families of priors. It's just that if you go into very specific priors, then you may be a bit stuck. While a Gaussian with actually, or a mixture of Gaussian is actually usually good enough. But it's tricky, and actually the Bayesian, that's why there is often a move towards more sampling strategy like MC dropout, etc., because training can be a bit tricky.
And I believe the same person, Walia, she also wanted to find out, she says, I guess she wanted to understand the differences between the MC dropout and the Bayesian, because she's not too sure about how the dropout is different in terms of if it's just a setting of a hyperparameter change.
So the main difference is that with the MC dropouts, what you do is you completely kill nodes randomly, while with the other, and it's an approximation of the Bayesian neural networks, but classically the other one will say I'm sampling for every single weight among that distribution of Gaussian with a certain standard deviation. So that's how that's different. And if for more information, actually, I would just encourage to go to that paper of Gal from Jan Gal from 2016, because there is quite a nice link with Bayesian neural network there as well. So for the details, that may be useful.
Perfect. Tap that. There's two more questions. Maybe if you want to just take them or move a bit through the.
Yeah. So let me check the time. We'll see afterwards. We may. So let's see what they are, and if I can answer, I do. Otherwise, we'll move on to the rest. And if there is something that I'm talking about afterwards, I'll let you know. Okay. Let's try it.
Okay, so this should be a quick one. As many standard models like the VIT ResNet use dropout, does it allow you to quantify uncertainty? If you use dropout on like a ResNet or transformer?
So there are different ways, right? Dropout at training time is usually to allow you to avoid overfitting and to have a more robust way of training. Here we are talking about dropout at test time. So that just need to be aware of that. Yeah.
Yep.
Second question.
Second one was they talk about papers from Ashburner and Van Lieput papers about Bayesian inference using atlases. And they're just trying to find out, is there some sort of go-to reference in terms of getting those basics right in Bayesian methods?
Go to the paper of Ashburner and Van Lieput. They are really good.
So that was, they know about those ones.
Yeah, if they're not those ones, that's, I mean, just, and go step by step, because actually those papers are really, really nice because they go step by step, especially if you read the appendices, they go step by step in the derivation. So that helps quite a bit, especially for expectation maximization type of things and how you do your priors and etc. and also the variational side of things. So unified segmentation in particular from John Ashburner and all the papers on bias field estimation and segmentation from confirmed input. Really recommend it.
I think we maybe continue and then we can.
Yeah, and then we see the other ones. So here what I wanted to discuss is more like the way we can measure things, because let's say you have all your samples, right? So we are at the stage where we have done all our sampling, but what next? How do we measure the uncertainty from there? And there are actually multiple methods that people have proposed for that. There is just the variance, so looking at which is a classical way of looking at the variability of your samples, but you can also look at the entropy or at the mutual information. And that's typically what you, when you do that, that's a toy example from a paper by Tanya Nair from Media 2020 or 2021. She got actually a Young Investigator Award from MICCAI the year before for the preliminary work of that paper. It's actually a toy example to look at how, according to the samples and the probabilities that you get, you may have different values of variance, entropy, or mutual information. And I'll let you see that for yourself here a tiny bit, where you see that, for instance, if you get all the time a predicted probability of 0.5, which you could say, well, actually, I have, it's very uncertain if it's a probability of 0.5, well, actually, the variance of your prediction is null, because it's always the same probabilities that you get. So try to think a bit about what variance mean and what how it relates to the probability itself, and what it means for your uncertainty. And just showing here what they did, which is actually quite interesting, looking at how this measurement of uncertainty and potentially dropping some of the, here they are dropping some of the lesions that they classify as uncertain according to a certain level of uncertainty, how that may improve their overall performance. So where we go back to that idea of if it's too uncertain, I need to abstain from things that it's something, or actually I'm very likely to make a mistake, so I won't take it in. Here at the level of lesion detection, lesion segmentation, but you could also consider it that, for image level classification. So that's that. And then I'm just trying to talk here briefly about different ways of ensembling in machine learning. And I guess, you have different ways here. Usually I ask that as a question, but we'll go on like this for time. So you can train on different samples. So the idea of ensembling is you get different samples output based on different type of input. And that's about leveraging all the randomness that you can have in your models. So you could say, I take different models and I aggregate their outcomes. But it could also be, I have the same architecture and I train it in different ways. So I train it on different samples, bagging. The problem there is that you may have worse performance if you are limiting the training set. So that works only if you have very, very large training set, probably. Well, that can work probably on other situations, but you may have a drawback here. You can train with different type of initializations, and obviously randomness in terms of the loading of your data and the presentation of your data. and training with different orders of samples. So it's about trying to leverage as much as possible the stochastic properties of model training. And that's what we'll do in the practical. So in the second part of the practical, what I've done is I've given you quite a few models. If you want, you can either use the models themselves or use the outputs themselves. But I've basically trained 59 networks to using a typical UNet style architecture on a subset. I've arranged a subset of the white matter dependency segmentation challenge. They have all been trained without any augmentation with a UNet, just with different type of initialization on to detect white matter dependencies, to segment white matter dependencies. And you can see what the output is in terms of die score, and then calculate the different measures of uncertainty we mentioned before. So variance, entropy, and mutual information. So we'll get you to start with that, to run whatever you prefer on it. You can also just go through the notebook itself if it's easier. And then we take questions, I take questions, and we discuss a bit, and then we'll go for a short break.
There are some previous questions, Carol. I don't know if we should also maybe.
I'm happy to chat about to discuss the question while people go on with the notebook in parallel. That may be a good one.
The first one was, instead of MC dropout, can we try getting probabilistic uncertainty of the prediction probability of a single sample? I'm not too sure. I don't know, Madi, that was Madi's question. I think maybe what she's trying to find out is, can you do kind of like the variation?
Is the softmax, for instance, just using the softmax? So people have said that actually the softmax may not be the best way of assessing the probability, that means the uncertainty. Yes, that's kind of a surrogate, but actually the neural networks tend to be overconfident. We look into that a tiny bit when we talk about calibration, and actually it can be used directly when you look at conformal prediction. So that form of probability and using the softmax values can be used in the context of conformal prediction. We'll touch upon it at the end of the session today.
Right. There's another question about your slides 18 and 19, the visualizations that you created. How do you do those? On slide
18. So let me check my slides 18 and 19.
I also forgot which was on there.
That's not me. That's the source of the, you have the source of that website. That's from there. You should ask them. I like them a lot. All the rest of what is from me is just PowerPoint, to be honest. So sorry, I can't help for that.
All right, so let's see, because I think the links are not on the site for the slides, but they should be there soon. Please, may you elaborate more on the link between mutual information and CE cross? What was CE cross
entropy?
Yeah, I guess so. Yeah.
I'm not sure what.
Yeah, I don't know. Anonymous. I'm not sure if maybe you want to raise your hand, but it's anonymous. I'm not. Entropy. So the difference between the mutual information and entropy in general.
So the idea basically is it's very related. It's just that one is using the average and you calculate the entropy over the average that you get. And the other one is you calculate the entropy for each samples and then you take the average, and that's what the mutual information is about. So they are both related to entropy, just in which direction and at which stage you take the mean.
I think that's good. Yeah, because I wasn't sure if it's the loss or that's cross entropy. Great. Yeah, so if you have questions, you can definitely, I think we're getting through them quite well. So, but it's quite a nice collab file that you have. Carol, I wish I had this when I was stuck in uncertainty. I was like in the dark.
And I'm really sorry if something doesn't work. Normally everything worked on my, local machine and etc. But I know it's sometimes a bit complicated.
There's a question as well. Okay. For your upcoming part, okay, this is preempting conformal prediction. Regarding softmax thresholds, generally it's 0.5. But do you suggest that this threshold should be varied during calibration for conformal prediction? But I guess I'm not sure. I think
We'll talk a bit about that. We can talk a bit more about when I go into calibration. So what I will do is probably leave a bit of space at the end for questions and further discussion because it's great that it raises so much interest. I'm really glad. And there are plenty of things that I don't know, so please bear with me. There are plenty of things that I may not be aware of, and maybe Taryn or others can also, present stuff, especially Taryn.
Yeah,
But
well,
she's a specialist of uncertainty, so if I can't answer, she will probably be able to. But we can discuss definitely that a bit further when we talk about calibration.
yeah, I can also give some insights from the doctors when they gave us that. There's also a question about, I think it's your pairwise dice function, where you were utilizing a threshold. It looks like output greater than 0.8. So I'm not sure if they're asking why was it 0.8?
Oh yeah, I was just random choice, just to make sure that you could change it for 0.5, no problem at all.
Perfect. Oh wow, this questions is coming in. I was trying to use the probability histogram of voxels to access uncertainty by calculating standard deviation and entropy instead of using Monte Carlo dropout, which requires multiple forward passes. Is there a viable approach for measuring model uncertainty?
So probably you refer probably to the solution in terms of more Bayesian neural networks where you predict the variance in addition. So, but usually, so for epistemic uncertainty, you still usually, so the algebraic one, you can definitely try to see what the predicted variance would be. That would be your algebraic uncertainty, but you would need still, if you go for the, you would still need a sampling strategy at some point, so multiple forward passes.
Someone says they have very bad issues. Well, I don't want to say shame, they're like very dumb issue, but running their Colab notebook. It's not mounted. I guess maybe you just need to download the CSV file because it says there's no such
Yeah.
file. You need to download it into your drive.
Yeah, probably. So everything is available on my drive, but then you need either to mount it or to download it. And there may be slight changes in the path, so be careful to get the path right. But if you download everything that is from the Google Drive, you should be able to find the files that you need.
Sometimes the other drive name changes, but I think that's fine. The last question here, Carol. Is there a link between test time augmentation and test time adaptation? Adaption. I'm not sure. I don't.
So for me, TTA is test time augmentation, not adaptation. Are you thinking of domain adaptation at test time? It's not what we are covering here. So it's a different problem.
PTA, I know, but I don't know about.
ETA here is test time augmentation. So when you modify your data, and here you will not, we'll look into that afterwards. So let's say, well, basically, I'm staying there for questions, but we'll reconvene afterwards at 3:30 for the remainder of the talk. But I'm taking my break here with you. If you have questions, for those who need a bit of a comfort break, we will restart the slides at 3:30. Test time augmentation is when, sorry.
4:30. Oh, you in the UK?
Oh yeah, I'm sorry, 4:30 for you. Sorry,
Working in the UK.
it's still 3:20 for me.
Yeah. So okay, for us it'll be 4:30. Sorry.
Yeah, 4:30 for, well, 30 past the hour in hopefully whichever time zone you are. Hopefully that works.
Perfect.
But I'm there for questions if you need to.
There's one that came in. Carol says,
Yep.
in the case of regression tasks, how could we address uncertainty?
Oh, that's something, to be honest, that I'm really less familiar with. But I think you could address it in similar ways that you have with a Bayesian linear regression, where you sample in the same way, and you have then multiple estimates for your outcome. And so you would get a confidence interval for every single of your outcome.
Yes, yeah, you can use entropy there as well.
Yeah.
Changes.
So in the same way, it's very, very similar. It's just that it will look at continuous variables in terms of binary variables or categorical variables. So it's usually trying to see what are the equivalent in terms of the continuous world.
I'll wait for you to drink, and then it says, is there a link between robustness and uncertainty?
That's a very good question, but it really depends on your definition of robustness. Is robustness, because you could say robustness is ability to sustain, changes or shifts in your domains, for instance. And it relates a lot to the data that you have been training on. And so, and again, if your model is actually looking at only a specific part of the data generation process, obviously, if you have a massive domain shift, you will be OOD, so out of distribution. And so you would like your uncertainty measurement to shoot up if you have not been able to train properly there, and if you are not able to measure properly the data features. So yes, and one way of assessing robustness would be to say, well, please abstain from using my measurements here because I'm highly uncertain. So yes, you have that link here. It really relates a lot to how you do and how you design your model and your training. And if you have a lot of augmentation, if you are robust to artifacts, for instance, if you have trained according to that, if your model is generalizable enough or not, and relates a lot to how much of the real world space of data generation corresponding to your problem do you cover. Because if you cover everything and if you are able to do everything, then you may not need uncertainty. But if you have limitation in terms of looking at specific area of the generation space, then yes, you would, and uncertainty is particularly important, and being robust enough to say, I can't be sure here because I have not seen that before is actually particularly important.
I guess, yeah, that then speaks to their point where they asked if you could say something is uncertain on a particular sample. So I guess that speaks to what.
Yeah.
Okay, that's perfect. There's one more. Okay, this was like where they want to say if you want to quantify the uncertainty map variance or entropy to a single score, what measurements do you utilize?
Again, that's tricky questions. There are probably, more recent papers that look into that. I haven't focused on that in my lecture today, but you can certainly look at, especially if you look voxel was, and you try to summarize things, because we'll probably discuss that a bit later in terms of open questions of visualization and sharing that information of uncertainty. It depends on what you're interested in. If you are interested in a specific region of interest, for instance, like if you are just interested around the hippocampus, let's say, or if you are interested just about a single volume. So what you could get is actually, imagine lesion segmentation, you are less interested in the individual segmentation measures, and so the uncertainty for every single voxel, but you may be interested in the variation in volumes that you obtain, because clinically what's important is the derived biomarker, which is lesion volume. And so you could integrate all your volume estimates on and your probabilities over the different samples, and get actually the variance over that biomarker. So that could be another way of going around getting an idea of uncertainty in a single way. Otherwise, you could, you have ways of averaging or focusing on specific areas, or looking at different stats methods in terms of what's the area that is the highest uncertainty, and actually you realize that it's at the skull. So you don't really care about that part because you know that you have methods that can take care of that for you. So it really depends on your context, and it really depends on what you want from it afterwards. Sorry, no clear answer, but hopefully that can help a bit.
You have uncertainty. There's a nice one. I guess maybe this is what we also struggle with sometimes, but they want to find out from your viewpoints and experience methods like Bayesian, dropout, sampling. They have different, your outcomes could vary in terms of your uncertainty quantification. So is there kind of, do you think that they produce like similar results? Maybe there could be one, I'll change it slightly because is there one maybe that's better than another from your experience in terms of, I'll say we see it, the quality of how we quantify.
So I'm more of a, I don't like choosing, so I like having multiple things. So usually what I do when I'm not sure is trying to see the different ones at the same time and seeing what they bring me. And so when I'm interested in one specific aspect and I know that it seems to work better, I'm choosing one over the other. But otherwise, I kind of like having, in particular, variance with entropy or variance with mutual information. Because I know, especially, from the toy example I showed you before, it was obvious that the variance was not covering something in terms of the uncertainty at some point. And so having the entropy there was very useful. And you will see when you go at the last bit, I mean, you are maybe close to that. At the last bit, I gave an example of the typical outputs that we get for that one specific slice of one case. And you see that it's actually slightly different across the different measures of uncertainty. And that's there that you actually stop and discuss. It's not to say one is better than the other in all cases. It's more like, oh, here I see that and I didn't see it in the other one. What does that mean? What does that mean for my model? What does that mean for my application? How people can use it? But yeah, I don't like choosing, so I put everything that I can.
I agree with you on that one. Maybe also because I also, even though MC dropout, it's known, we always will keep it there, but we'll always use other ones alongside it. Just want to see what it does. So.
And we'll see a bit. I mean, I will show you a case of another network, the probability unit, to look at generating multiple possible outputs. And you see that the difference in particular with MC dropout is that MC dropout is kind of blurry, but they all look relatively similar. While actually there may be other ways that allow you to have different modes of segmentation output. And so thinking of different training school in particular and different ways people can produce outputs. Again, going back to one of my first slides on the variability of annotations.
I guess maybe we'll take one more question, Carol, and then we can.
And then we start again.
The last one is, okay, this is one of those ones again. We kind of, what's the best strategy to use to understand if a model is suffering from aleatoric or epistemic uncertainty?
So my go-to tool to understand that is telling myself, if I add more data, if I understand more about the data, will it be better? Will I have a tighter confidence interval? And that's what epistemic uncertainty is about, is if knowing better where the data come from and how it's organized and how it's, how it covers a world of possibility is better captured by my model. That means that it was a model problem, and that's epistemic, that's from knowledge. If it's just because there is measurement noise that I can't do anything about it and I can't get anything about it, I can just assess what happens, and that's aleatoric. That's the randomness I can't do anything about.
Perfect. That's good.
Okay, so I will get started again. And then again, I mean, if there are questions that you think are related to specific slides, please do share them. Right, so we were at the ensembling one, and this is also a very critical paper looking at ensembling and showing how ensembling and different ways of looking at use of probabilities can help, especially when you don't have much data at the tails. And now I'm talking about other ensembling methods. So in particular, mheads, where you have a similar extraction feature type of architecture. And then at some point you diverge into different heads that could correspond to different training way or could represent, and hopefully they diverge slightly into different solutions. And usually when you calculate your loss, you start it and you propagate it from the best head, so the one that has the best performance, and you add a bit of, but to a very minor fraction, what's happening in the from the other heads. And so you can apply that here for PET-CT reconstruction and attenuation correction, where you have what happens here, where you see here the difference between what happens with MC dropout and what happens when you do a multi-hypothesis type of framework. And then the next thing is the test time augmentation and the MC dropout, and where it's here how the output change if we change the input slightly. So it's slightly linked to adversarial training, but one of the questions I always have with test time augmentation is, are we actually showing aleatoric uncertainty, or is there such a difference because our network is poorly trained? And so that's something to keep in mind sometimes, because that may be a bit misleading. But here is an example where they looked at fetal brain segmentation, looking at, again, MC dropout and aleatoric uncertainty with test time augmentation, and where they constructed a hybrid uncertainty with the two of them. And so now you can go and do exactly the same as before, but with the test time part of the notebook. And what you will see here is that actually it's we're looking at, I just would like you to look a bit at the type of augmentation I chose, and if you have any comments on why I chose this type of augmentation in particular.
Well, there's a question about slide 33. I'm not sure. I think maybe they're just checking to see the reference paper for that one.
Did I forget it? Oh, I'm sorry. It's Wang et al. From 2019.
I guess while some of them are looking at that, and some are, there was I guess a nice question. I don't know if it's gonna come up. I think you might get to it, but it's the kind of thing where you want to measure uncertainty. What can you do with it afterwards? Do you change the model architecture, or do you redesign that and see if it gives you a better uncertainty or less uncertainty?
That's a tricky question because it depends massively on what you want to do. So, because you could say it depends on, so if you could say, actually, I'm happy with what I have and I won't be able to do much more, but I need to be able to provide that information about uncertainty. And in that case, you just try to make sure that your uncertainty assessment is as good as possible, and that indeed you flag cases where you can't know, because they are the ones that, especially in a clinical workflow, are very tricky. You don't want to make mistakes while being sure about your assessment. So that's what you really hope not to get, because that could have very, very serious impact. You could, if you think, actually, no, it's just not feasible for a clinician to do, you need to consider it in the perspective of potential clinical workflow or clinical translation of your model. And if you realize that your confidence interval is always really, really broad and gives you non-usable outcomes, then there is probably something wrong about either your training, your model, something, and then you need to probably go back to the whiteboard and think again. Either in terms of data, in terms of, training itself, in terms of quality, whatever. There may be something else.
Thank you. Perfect answer. Yeah, I don't think there's any, I don't know if anyone's got any questions on this part from the Colab notebook, but
it should be very, very similar to what you have seen before. So what I wanted you to check is actually when I chose the augmentation, I chose augmentations that were not changing the geometry of the labels. So I chose just deformation, transformation of in place of the image. So just noise, bias fields, motion, and other type of acquisition artifacts, but there was nothing related to rotation and etc. Just to avoid actually the labels to be modified too much and to not be able to be in the same space afterwards. Because otherwise you can't compare.
yeah, sorry, no, they were just asking about the slides, but they will be there. I guess I'm not sure if maybe give them another minute, Carol, or do you want to?
I'll give them another minute. I mean, we are.
Okay. Someone asked about the link for the notebook. Okay, I thought let me just put it into the chat.
So it's the one that is called Uncertainty Rise IPYNB. That's right.
Yeah, I'll put it there and I'll also say it there. There's
there's another question.
one question. Maybe we take this one. This one says, regarding the use of dropout, it's usually enabled during training and disabled during the testing phase. When applying,
Not with uncertainty.
that's this one says, so when applying dropout for uncertainty, should it be enabled again during the testing phase to run multiple prediction estimates?
Yeah, so that's exactly that. So the difference, the use of MC dropout is, as you will see, we've seen that in the slide, it's a stochastic at testing time. So it's allowing dropout at testing time. What I was mentioning before, the difference is like classical use of dropout is at training only, when it's to make for more robust training and avoid overfitting. But in our case, what we want is sample at testing time, because we want to, apologies, aggregate samples afterwards. So we need to sample and to have multiple outputs at test time. And so that's why dropout needs to be on at test time if you want to do it.
All right. I think maybe we can.
Yeah, we can start again. So now we'll focus a bit more on probability unit and try to show you that specific case and algebraic uncertainty related to that. And then we will move on to more calibration, conformal prediction. And the last part, we'll just leave it on for question and general discussion. So I'm still good on time, so that's fine. Great. So we were there. And now just talking about labeling uncertainty, where labeling can be massively different across graders. So here another example that's taken from the probability unit paper, where you have actually, they're looking in the lungs, and some graders are not, annotating something massively differently, and actually one grader even didn't find anything while the other one did. And that you have that across all, I would say across almost all fields of medical imaging, where actually getting annotation is very, very hard. It's very time consuming, and it can be very variable according to the expertise of individuals and according to, well, their perspective and their representation of the data. And the main idea behind the probability unit is actually the idea of trying to create a distribution in a latent space of what the segmentation could look like, and be able afterwards to sample from this to create possible segmentation output. So you create the low dimensional space. You try to see where your image fits there, and then you propose across that distribution different side of segmentation that could come, and then you create those. And you train it by actually making sure that on one side you can sample from the different segmentation, and you put that in a specific latent space while you put only the image on the other side. And so you have your predictive segmentation, and you try to get it as close as possible as a ground truth segmentation, while at the same time minimizing the difference in the two latent space of what corresponds to the segmentation from the image that you have and what corresponds to the segmentation itself. And the interesting aspects here, and what's actually quite nice from their paper, was one of the first paper looking into those type of approaches, is comparing what happens when you have ensembles, when you have dropout, and when you have that probabilistic unit, and when you have M-heads. And you see what I was telling you about before in terms of dropout, you have a lot of speckled noise actually all over. In the unit ensembles, well, you get slightly different proposals, but they are roughly very close from one to the other. In the M-heads, you may have a bit more variability, but you still don't have anything where there is one missing annotation. So that may happen quite a bit and a bit too much with the VAE, and then you have much more variability in terms of the representation, and also in terms of the presence absence that you can have in terms of the different proposed segmentation. And there has been quite a few other methods that have built on that, or use similar ideas to also propose and work around annotation in general. So now we'll move on to the last part of the talk, which is really looking into trying to think about calibration and conformal predictions. I won't go too much depth into it, but we can discuss a bit further afterwards. What I mean by calibration first is thinking of the probabilities that is output, and thinking that actually what you need is to make sure that the probabilities that you predict correspond to your chance of being right or wrong. And what people have seen a lot with neural networks is that there is an overconfidence in terms of the distribution of your probability, and you tend to not have like uniform or but a distribution of probability, but really distribution of probabilities that are peaking at either 1 or 0 and a bit less of things in the middle. And so ideally, if you have a probability of 0.7 for the 10 prediction, you should be correct 7 times out of 10. And that's what you're trying to look at when you look at this calibration plots, where you look at your accuracy. So how often are you correct in terms of your prediction? And you look at that with respect to some bins of prediction. So you could look at all the prediction between 0 and 0.1, and you should only be correct 10% of the maximum 10% of the time, or the average of it. And so you compare your accuracy versus your confidence over that bin of predicted probabilities. And you can build that plot and try to calculate what we call the expected calibration error, which is the absolute difference between your accuracy and your confidence in that bin, and you sum that over all your bins. So it's typically relying on the number of bins that you are choosing. There are quite a few hyperparameters that you need to take into account. It depends also on, it may be impacted by the distribution of your weights, especially if you have very, very few samples. in certain bins, and so you have had a specific adjustment of that to account for the difference in distribution and to adjust for this. But that's typically the idea here of the calibration error, is trying to understand how far am I from the straight line, diagonal line, when I compare my accuracy and my confidence. And you can also do that in terms of at your maximum. There are other methods of calibration which tend to use both the performance and the calibration at the same time. So for instance, the Brier score looks into that. So it measures both how good my probabilistic prediction are versus how good am I performing in terms of the classification that I'm looking into. So you are looking here at what's my probability. Here is the FTI with respect to my output class for that specific sample. So you get both at the same time, and sometimes it's slightly difficult to disentangle what means what and what corresponds to calibration, what can correspond to the performance itself. And then they have obviously calibration techniques. So people have looked into ways of slightly shifting or modifying the probabilities so that they fit better in terms of the histogram. So you can potentially do some binning of the histogram where you adjust the value of the probability for at each level. You can do a linear regression specifically on each bin as well to readjust the probabilities there. You can do temperature scaling where you are transforming the logits with the multiplicative factors. And then you can obviously tune your hyperparameter on a validation set. So you would need an additional set to help you calibrate your model. And you have that as well with splat scaling. So those are additional methods that you can potentially use to help with calibration. It can be very tricky, but it's also very important because if your model is non-calibrated, actually that means that the probabilities that you are outputting are meaningless, and that can be problematic. Any questions so far?
I think we have some questions, but it was probably to do with the segmentation. So I guess was that if you want to look at, trusting the output of segmentations and utilize those scores, what scores would you utilize when you're looking at those uncertainties? So I guess it speaks to that slide where you're showing all the different segmentations to understand which one.
So then actually what you do is you look at the distributions. And so usually you look at the Kullback-Leibler divergence or ways of measuring the variability, and you see whether you fit in terms of distribution of expected segmentations. So it's slightly more complicated in terms of how you perform your evaluations of representation. So what you're trying to look at is your proposal proposal representation of distribution look alike with what you expect from multiple raters.
Okay. I guess maybe we can go back to that other question but I guess you were asking about calibration and conformals. I don't know. We can talk about the thresholds now, I guess. When
you want me to maybe I go through the conformal bit of thing. Let me go through the conformal bit of thing. It won't be very long, and then we stay a bit longer to discuss further. All right? So here was, different methods and what you can do in terms of calibration. There are a lot of other things that you can do. This is just a, starting point. Here is also another way of potentially looking at quality of your uncertainty, where some people, and that's a bit debatable, and we can discuss further what that means, where people say, well, actually, in the places where I'm uncertain, I'm much more likely to make mistakes. So I should have some form of overlap, and looking at the overlap between my errors and the high uncertainty. So obviously you can calculate it at different thresholds of uncertainty, whether it's you normalize your variance according to your variance levels or your entropy and etc. And you identify your true positive uncertain, which are the one, especially for segmentation, the ones where you have high uncertainty and you have a segmentation error. Then you have the false positive uncertainty, where you have high uncertainty, but it's correct. And the false negative uncertainty, where it's segmentation error, but you have a low uncertainty. And you can calculate some form of a dice measurements of your uncertainty in terms of your true positive, false negative, false positive. There is some limitation with that type of measure, which is that, yes, you may expect some errors, but it's not. There is also some levels where you may have, and that relates to calibration, where you may have relatively high uncertainty, but it's still correct. And it's not wrong to be correct and to not make mistakes even if you are uncertain. So you don't always expect to be wrong when you are uncertain. And that's what this type of measure doesn't account for, and it's probably to I mean, it's fair to use it, but it should be used carefully and should be commented carefully. So again, sometimes we don't have the proper tools to assess things, but we have surrogates, or we have things that work to a certain degree. Fair enough to use them, but they need to be taken really carefully and discussed properly, and especially those type of questioning where actually it's not because it's not making mistakes that the uncertainty is wrong, or that that should diminish the quality, should be taken into account. So now moving to conformal prediction. It is a field of uncertainty that's taking a lot of momentum because it's relatively straightforward. The principle is quite clear, and it's relatively easy to extend it to multiple contexts and to multiple tasks. The idea here is that compared to a lot of other methods where you are assuming something about the distribution, Gaussian sampling, etc., it's you don't need that. You don't need to do multiple sampling. You don't need to do multiple runs. However, what you need is a calibration set to decide on your threshold and your definition for your quantification of uncertainty. And I will go step by step with you through that one. You have the reference to that paper. That's probably one of the best paper to start with. It's called A Gentle Introduction to Conformal Prediction from 2021. And it has all what you need to get started with conformal prediction, and then you can move on to more complex things. But that's probably one of the key picture of that paper, where we give you kind of the recipe to understand what it means and how you get on with calculating things, and then you can do it in the notebook as well. So the idea here is, especially when you have multi-class classification problem, is to tell you not that you are that amount certain of being of classifying something as a specific class, but that actually you will have, with a certainty at an alpha level, so 95% for instance, you are 95% confident to fall into one of two classes, or one of three classes, or one of four classes, or more, or just one class. And that's, you calculate that based on the distribution of your probability scores. You get the quantile variation. You take 1 minus that, and the value that you get, and all the classes that are being classified with above that probability will be in your possible set of prediction. And then you are at 95, if your alpha is at 5%, you are 95% sure that the true value will be in that set. That clear? It's a very simple recipe, and it's quite powerful because it tells you, what can you tell afterwards? Well, if you end up with only one variable, one possible class, that means that you're actually very, very certain, and hopefully you're right. That's what you check with the size coverage matrix here. And if you're way more uncertain, then actually you may have probabilities that are very similar across the different classes, or you may have two classes for which the probability are quite similar. And yes, one is slightly higher than the rest, but when you look at your 95 confidence interval for those, it's actually so similar that they would be one or two the same ones. And that helps you as well understanding across classes which ones are more likely to be classified together. So you could imagine, especially for some form of ordinal classification, cancer grading, for instance, or cause diagnosis, etc., that the closer one from one another may be more classified together than the other ones. And that helps you afterwards understanding how uncertain your data is, how likely is it to make confusion between specific classes, and potentially then to think about retraining or stratifying or doing something else about your models. And one metric that you have is a size coverage metric here, where you are actually trying to calculate the percentage of time that indeed the true label is in your predicted label set. And you take the minimum across the different set of labels that you can consider. So in the paper, they were considering only one value up to 2 classes per and 3 or more classes. In the examples that I gave you in the notebook, we did with all five classes. What I'll do is that now, so that's I think my last slide on conformal prediction. So you can go on to do the practical, and then we'll discuss a bit more about, generally what I've said, and take more questions. If that's all right.
I guess maybe that's a good point. Maybe I can raise the question about the conformal predictions that someone's asked. So they said regarding, I think it's just your last slide where you're looking at the compute scores. They want to find out if that's referring to non-conformity function to calculate the score, or can you also explain a little bit more about non-conformity function? Up on the slide, and they were regarding that compute score slide. That's
the compute score has a predicted probability, so that's your softmax.
Yeah, so they were talking about non-conformity function to calculate the score. I don't know if there was something wording there that
I'm not sure. I'm sorry, I'm really not sure here.
But maybe not sure if she wants to clarify the question. I got the answer. Okay, she was saying that it's related to softmax. Okay.
Yeah.
Okay, that's perfect. And then there was also actually when you were busy with the conformal predictions, but I guess maybe this was where someone wanted to just find out if you have uncertainty and you're looking at calibration, could you have low uncertainty, and does that mean that something's well calibrated? I guess that speaks more to the reliability diagram.
Yeah. So that's always tricky, because the main issue that you have with this calibration plot is when actually part of the distribution is not represented. And you have actually some bits that are completely empty or close to empty. And you're a bit stuck, because actually all those error measurements, they were great if you have, if you distribute well across everything. But if you have some parts that are completely missing in the distribution, you cannot invent it. And having low uncertainty everywhere, it doesn't mean that you are poorly calibrated. If you are actually indeed performing really well with low uncertainty regimes, that's totally fine. It's probably because either you don't have the correct sample to test on to see what happens when uncertainty can be raised, or actually you have the perfect model. I would be more inclined to say that you don't have the perfect model, but you probably don't have the perfect data to test everything on. But that's a difficult question.
100%. I guess this one is kind of depends on the situation, but should you calibrate the model during the training phase?
So no, so that doesn't happen at that stage. You calibrate after you have your validation, so you adjust. It's not with your training that you can calibrate. You calibrate with your validation set, but don't calibrate on your test set. And maybe have actually, separate your validation set in different subsets. right? You keep your trainings that just for your training, and then you have a small validation for calibration and validation for other hyperparameters.
A good point. They were kind of asking if there's some introduction book that they can use for uncertainty. Some book that you think that's a good one just to get them.
I've cited a few papers in those slides. Those are very good reviews, like the meta-radiology one, or very introduction papers like the Angelopoulos one. So I've cited more like the key paper that I think are interesting and got me started with uncertainty. So those are the ones that I always go back to when I'm a bit unsure about something, especially when someone raises something new and I'm a bit like, oh, I need to go back to my basics. Those are the ones I go back to. But that may be missing from me looking at the literature. I've not looked at books specifically.
I think it's because you're so used to the papers, I guess, as well. Then there's one, okay, they were applying to other person to tell them they can use a practical guide to apply conformal prediction in Python. They were helping someone else.
That's great.
And then
And actually, that's good in the gentle introduction to conformal predictions. They have all the code online as well, and they have all the code ready. So if you want to use it, that's actually pretty useful.
perfect. There's also, I guess now we can go back to that other question about looking at different thresholds and how does that then apply in terms of doing it for conformal predictions and choosing those certain thresholds. How does it work?
So with conformal predictions, that's the nice thing about conformal prediction is that you don't need to choose a threshold in some way. You choose your confidence interval, and based on that, you will get what is your threshold. So that's why you have that calibration set that you need to do your stuff on, and then you will use that value that will become your threshold for your softmax prediction for the calibration set.
Perfect. This one, I guess maybe more on the data side, but if you kind of have a small data set, what do you do in terms of splitting that data with train test validation?
So that's always tricky, right? And that's probably where conformal prediction may not work as well, is that you need that amount of, you need a certain amount of calibration. And otherwise you won't get an appropriate threshold assessment. So you will probably need to go more to multiple sampling, test time augmentation, MC dropouts, and etc. Because first you will probably need dropout anyway because you will have overfitting, and that will be complicated. You probably use then methods where you rely less on or full test set outside that you can't use because you cannot use as a training. So yeah. It's always a balance, right? And usually you choose one design versus the next because of the constraint of your data.
Yes, perfect. It actually looks like we went through quite a lot. I think you went over like maybe 58 questions.
That's it. That's great.
That's
Well,
I don't know if there's
so we
more.
just let people work a tiny bit more on the conformal prediction if they have the time. So on that one, it's again a very basic, basic task of we're using some extracted measurement from ADNI. You have a random forest and you have a neural network, mini things like toy examples that you should be able to run relatively easily. And then we look at conformal prediction and size coverage metric.
It's a really nice notebook. Can I use it for myself?
I was thinking of using it for other teaching material actually, because now that I've put the effort in trying to create something nice.
Will they use something similar at the MICCAI workshop or
No, we don't. So maybe, and I'm not helping with the tutorial, but
this would be nice.
but yeah. I'm happy for people to use it, honestly, as long as you refer to where it comes from, that's fine.
Oh, okay, there's again the small data sets. Can we use cross-validation to calibrate the model?
That may be difficult because you may need. Personally, I wouldn't do it. People may argue against that, but I wouldn't do it just because actually you will get you will have a different model each time. So it won't be, you won't be able to use that model afterwards as a whole.
There was another comment. Is there a guarantee that every model can be calibrated?
I would say no. I'm not 100% sure, but I would say no because I've looked at examples where I tried, to even on very simple things like basically the ones that you are working on right now, where actually we tried temperature scaling, we tried plat scaling, and actually sometimes it was making things worse. And it's just because it's very badly distributed. Your model doesn't fit properly, and yeah, things where it just can't work as well as you could. So that's where you need to try different things and see how close to that straight line you can go. But then looking back at the distribution, saying, well, actually, I'm limited by the type of bins that I have or the type of presentation of data and output that I have, and that's where actually instead of calibration, you go to the conformal prediction side of things to say, well, actually, instead of going for just making my prediction better or my probabilities more aligned and trying to trick them into some form of a weird wrapping, I would just move on to something where I'm like, I don't know, but at least I know between 1 and 2, or at least I just don't know anything and I just know between 0 and 4. And so that allows you to spread that. That's shift to conformal prediction. It allows you to shift back from the individual class prediction to a more like very certain that it's that answer, or way less certain that it's that answer, and I don't know across those and those. And so thinking more about how you express it also in terms of usefulness for clinician, because the first one would be, I'm very certain, I'm very uncertain, but then yes, but that could be what? It's way more interesting to tell you, especially if you go back to the first examples that I gave you of application when we are looking at migraine and stroke. If you were to use that for conformal prediction, typically in the second case of the elder person that had stroke, had a headache and potentially other clinical history of blood pressure, etc., for which we had a good 20 per 0.2 probability that it was stroke, then it would be typically, I have two possibilities. Yes, I lean a bit more towards migraine, but actually there is the second class that I'm considering is stroke. And so yes, you do those tests for stroke. So where you see actually the practical utility of having that instead of having your main estimate saying, I'm a bit uncertain about the migraine, but not giving you any further information of what else it could be.
Yep. There we go. As soon as we're done, one comes up. How can we calibrate fully? Okay, so let me just say it. How can we calibrate? So how can we calibrate a fully connected CNN? That's what I understand, as they don't have linear if fully convolutional layers, which are usually used for calibration. How do you normally calibrate a fully convolutional model as they don't have linear FCL, which are usually used for calibration?
Because what I'm thinking of in terms of calibration is the final prediction output, the predictive probabilities that you have. So it doesn't matter really what happens before. It's just the distribution of what you get at the end in terms of the probabilities that you are looking into. So the type of model doesn't matter much, because what you do for the calibration, especially for your calibration set, is looking at how you need to shift those probabilities and which one need to either shift a bit up or shift a bit back to try to be as close as possible to that diagonal line in terms of your predictions. So I will just share my last slide in terms of summary to discuss a bit, and then we can discuss a bit more challenges and application, and we have maybe a 15 minutes of discussion if there is the need, and otherwise we close early. Right. So hopefully now and probably some of you knew a lot of what I've discussed. Some of you maybe have known a bit less. Some were discovering everything from scratch. I have no idea, and that's great. But hopefully you have now a better idea of the multiple reasons why we need uncertainty assessment and we cannot just dismiss it. You know a bit better what we mean by the different sources of uncertainty and different ways, especially between the aleatoric and the epistemic uncertainty, what it means to be homoscedastic or heteroscedastic, what can happen when and what can we do about it. I think the main point, and I think I try to teach that lecture around the idea of sampling, around the idea of moving from point estimate to distribution and different ways we can assess distributions. We've seen it with Bayesian networks, we've seen it with ensembles, you've seen it a bit with test time augmentation, but each time is the idea of having multiple samples or having an idea of the variability, which with what we had with the distance aware network and deterministic models. And then we had a bit of a smaller part on calibration and why actually the probabilities that you are predicting are important and how you can or cannot use them to assess uncertainty and to use them for uncertainty measurement. We discussed also a bit about all the different methods to aggregate these different sampling strategy and distribution strategies. And what remains is actually a lot, because it's a lot in terms of how do we visualize, do we summarize the uncertainty, and I think we have touched a tiny bit about that during our discussion before, but it's also how do we use it, do we transfer that knowledge, at what stage is it useful or not, is it at the development stage, is it to understand better and we were talking about retraining networks, is it at the stage where you translate your model into a clinical workflow? And if so, how do you do it properly? So I think there's still quite a lot of work to be done, and a lot of, both on the modeling side of things, on the modeling / application, because different applications may have different requirements in terms of uncertainty, and also in terms of trying to communicate that uncertainty in the most useful way, instead of having something on top that nobody is using, but is where it becomes just the elephant in the room in some way. So I will stop there, but we can discuss further, and I'm happy to think a bit more with you about all those things.
Perfect. Thank you, Carol. I think you're doing really well with answering questions as you go. So there's still, I don't know, maybe if there's something from the notebook or anything.
Yeah, maybe that,
practical.
I don't know how, it may have gone too fast for the notebook. I don't know. You want to go back at certain things. So maybe leave you 5 more minutes to look into things and to raise things.
We have a question. When we have different size coverage for different patient cases, how might we communicate its clinical relevance to medical experts?
With respect to what? To set coverage in the conformal prediction side of things?
Yeah, I'm not sure. Yeah, maybe.
Yeah.
Yeah.
So, it really depends on how you use it, right? You could say you could invent, it's to be invented, I would say, for every single application. It's probably when you could imagine that if you know that you're actually very well calibrated, you have low uncertainty, and you have things that don't require much triage, you can go on with it with minimal interaction or just junior checks, or less checks. When you have multiple options, it's probably afterwards that we can discuss about interpretability as well, is why, linking uncertainty with interpretability and trying to understand why certain classes are mixed up together or proposed as outputs. And I think that could be a very, very interesting way forward, not just uncertainty on its own, but also the the explanation of it and trying to understand where that comes from. So, for instance, saying, well, from that presentation, I'm actually looking or considering these specific features or this combination of features to guide me towards this type of decision. And then that can probably prompt further the clinician to either do some tests or decide between the two. But I think sometimes people tend to separate and put things in silo because we like putting things in categories and etc. But there is actually kind of a continuum of work, especially when you think of the translational and clinical aspect of things. And it's actually quite interesting to think of other ways of looking at the data that may be relevant and may help each other. So especially putting uncertainty and explainability together may be a good way forward.
Thank you. Oh, you got something nice that you apparently the most popular session this past week. Someone made a comment, so well done. Oh, that's nice.
Thank you.
I'm sure. Then a question about, can you comment on how much the medical field is addressing uncertainty compared to accuracy in practical applications?
So I'm not a specialist for that, just as a disclaimer, because what I just know is that it varies a lot from one country to the next, first thing, because you have very different regulations. And it's very difficult to actually get radiology-driven medical devices related things out in the market. So you have things that exist, but actually it's often, so I was looking the other day actually on the regulation for Europe and for the US and the need to provide confidence interval and to be at least within the confidence bounds that others have proved before to be approved again as medical devices. So there is actually literature on the regulations on what's needed and especially on the confidence intervals. But that's, and again, they are explaining a bit more what they request in terms of accuracy, so in terms of performance and the confidence intervals about the performance. So, but that can be, you can see that as the uncertainty of every single output, or as well as the variability of your performance across a large set of data. So there is sometimes a confusion in terms of the variability and the confidence interval of your performance, in terms of, the point estimate that you will have and the variability of the point estimate across a large set of data that should represent kind of all what exists in the world, hopefully, but never. And then with your own confidence about each of those estimates.
And then there's one where someone wanted you to please elaborate a bit more about quantifying the variability around a metric using bootstrapping. So with respect to standard error, I think for standard deviation, I noticed that standard error frequently led to smaller estimates. Could you?
Yeah, no, so it's because you are looking at the standard error of the mean. So you are looking at, it's not the standard deviation of your population. And you know that the standard error is your standard deviation divided by square root of n of your sample, usually is that, if I'm not mistaken. Please forget if I'm saying something wrong. But what you are doing with the bootstrap is you are actually looking at that calculation of the mean, and you are taking your statistics over that estimation of the mean. So you are doing that estimation of the mean multiple times, and then you get the mean of the calculated mean for your different bootstrap sample. And then you get, the standard deviation that you calculate is kind of the standard error that you have for that mean.
Correct.
Hope that's clear?
I think it was clear with me, so hopefully if you ask again, that's no problem. Someone said she'd like to thank you for your time. The best presentation for last. But they wanted to find out, Carol, if they wanted to maybe reach out to you in future. I don't know if it's via LinkedIn or what's the best way for you to.
Usually email is easier because, and you can definitely, if it's, I don't know if it's shared on the program or anywhere else, but I'm happy to share my email address. And otherwise, what I'll do is that I will update the slides so you have my email address there.
Perfect. Yeah. And then we'll upload those back
Yeah.
onto. Perfect. Thank you. Next one, given that different techniques can be applied to address uncertainty in segmentation, is there preference for any of them, or should they be used together to explain uncertainty?
Personally, I would go for a mix of both. First, because I don't think there is one that explains everything. And especially, you know, when we go back to that toy example that I showed you about. And for me, that was so striking that I always keep it in mind for my students, like the variance versus entropy thing for the toy example, where we saw it's very different. And for so that means that there is a meaning behind that is quite different. It's also relates to how you understand your data. So sometimes you will realize that your data, for instance, especially I'm just talking about stuff that I know, very small lesions. You can have and large lesions with a border. So what you saw in the tutorial was that we had quite a lot of variability at the border, you know. That's very likely to be the area where people, you know, where your model will be a bit more uncertain first because the signal is a bit less clear. And then if you have multiple end data that's there, that they will disagree. And on the small bits as well, because the small bits are the small lesions that can be completely missed or completely taken in, depends of the model. And you may have, you know, the specificity of your data will guide you to saying those are the kind of cases where I know that it will be uncertain. And so I will try to actually choose the metrics that may reflect, you know, where actually when I plot it, I see those happening more clearly. And sometimes it will be entropy, sometimes it will be variance, but it's kind of a feedback loop, similar to a learning process, right? Where when you design your first model, it works, but not as best as you would like. And so you look at the failure cases or at the weird cases and you go back and you try to make it better. I would say similarly with uncertainty, you need to look and to try to understand what it means. So it's a lot of interpretation of the maps and what they mean and what they relate to, and thinking of the errors that you get, thinking of how you can express it in terms of, you know, in words. What does that mean? Yes, like I told you, I have uncertainty at the border because the signal is less clear. I may have partial volume. I also have issue with the small lesions, and I want to be able to get that. So it's that feedback loop between what you get from maps out of the blue and how you can further improve them to express better what you want the data to say.
Perfect. Makes sense. Someone's mentioned, I don't know about this loss. I was trying to just quickly Google, but it's the Tursky loss. It's something to do. It's a loss
Tursky
function.
loss, yeah.
So in image segmentation, they want to find out if you proposed that loss.
No, I didn't. I did the generalized dice loss, if people are interested.
So they were just smiling and asking that question. Then how do we explain the difference between the X with the confidence interval and X over PM standard deviation standard error? Can we use the difference in the confidence interval to approximate the standard error or standard deviation?
Don't take my word on it for that one. We will need to go back to a bit of the stats there. Usually, if you have a Gaussian distributed element, you know that your 95 confidence interval is mean plus 2.96 of the standard deviation. That's typically how you calculate it. But it's with when you approximate it with a Gaussian distribution. So it may also vary if you have a non well distributed variable.
Makes sense. Someone asked how to fine-tune the hyperparameter as it may affect both the uncertainty. I guess when you're trying to train your model and you're trying to look at how it's affecting your uncertainty accuracy, how do you ensure that?
Well, that gets really tricky because you need all your different sets, and usually you assess so the thing is that you assess the epistemic uncertainty. It's once your model is trained, so you don't change your model anymore, right? You're at the stage where you perhaps converge towards something and you test how much uncertain. So how bad modeling at modeling is your model in some way, especially if you're focused on the sampling and the epistemic uncertainty. And so it's not, I mean, yes, you could have different model tuned, but in some way you could also say, well, I have different model tuned with different hyperparameters, and I'm considering them as different models of an ensemble. And then you can get somehow another form of uncertainty across the different models and across the different hyperparameters search that you have.
Would you think, well, this is my own question, would you think about, because, you know, I was trying to do that uncertainty awareness at one stage, but it only works to a certain point, because then you kind of get capped out.
Yeah.
So that's, I
Yeah.
guess. Here, can you please explain again how the H heads works?
The M heads? Yeah. So M heads is typically something like you have the same architecture of the network, and at the end you diverge in multiple possibilities, and they will all be initialized with different weights, and so they will provide some slightly different answers. And what you do is that you take the one that is the best, and that's the one that will drive the most the gradients backwards. And it's not that you completely ignore the others, but you use them only to a fraction of the gradient update. And each time that you have a new sample in, you get gradients from the best of the heads. And at some point, I mean, over the course of the trainings, those heads will diverge more and more. And so you get some, as if it was different schools of training and of their segmenting or doing something else. If you read the probability unit paper, they are referring to the main papers on hem heads. So from there, you can get back to the bibliography on hem heads if you're interested.
Okay. There's no more questions, but I'm not sure. I think you also wanted to end at about 5:30. Oh, wait, one last one that came in. The dropout model, on which parameters does it depends? Oh, I guess they're trying to find out if it depends on a point as a weight, but I guess it's the probability. So, but yeah, yeah. So they just, I think they were saying which parameters.
So you have hyperparameters, obviously, with the MC dropout, which is the probability at which you decide to drop your neurons. And also the other thing is to remember is on which layer you decide to apply your dropout. And that matters as well.
That's perfect. There's nothing else. I don't know if there's any more. I think we've really gotten a lot of questions today.
Hopefully that's been good, and hopefully you have the notebook, so you can go through that in your own time. I'll probably update the slides next week or so to make sure that you have all the references if you want to go back to that. And yeah, I'm happy to get emails if people want to reach out.
Thank you, Carol.
Thank you very much for having me, and thank you for all the great questions and discussion.
Yes, thank you so much. It's very nice to be in a more comfortable position this time. I think the last time
definitely. But thank you also for sharing and for guiding the questions and monitoring, because that's actually very important and very, very helpful.
When I saw uncertainty, I said I had to be on that one. So and it was you.
Thank you very much, Lauren. Thank you very much for the attendees and the organizers.
So much for coming. Thank you.
Bye.
Take care. Bye.
Bye.
I think we'll also just continue since we finished a little earlier and Carol has a shorter break. I think Uduna's only coming back for hers at 6 o'clock. So you get to have a little bit of a longer break. Maybe, I'm not sure if it's the same for you, but dinner, if that works. So we'll see you again soon. Thank you.